Prova. Sa. Okay.
Good morning, everybody. Thank you for coming to this morning session. It's for me a pleasure to introduce you Professor Eldar Karpinar from Atalim University. He's an expert in nonlinear analysis and physics point theory. And the talk of today is a journey through distant, recent advance in metric physics point theory. Thank you.
Yes, thank you so much for the introduction, Mr. Chairman. I would like to thank you also, Professor or friend Paco, for his kind invitation, and Pina. Today, I'm going to talk about a little bit distance and the corresponding what geometric geometry or just fixed point theory. Actually, our story is very easy. We have just 2 points and map maybe. So they have image. So we have actually 4 points. And then we will just consider the distance about this 4 point. And all fixed point theory actually just discuss about the possibilities of these 4 points. And I just say distance, so what you understand from the distance can be changed. So according to this, what change, the structure is changed, and we have a fixed point theory. So in brief, this is the my talk, but we can just go through to some detail, some historical background. Okay. Uh, yeah. So fixed point is clearly means that if a point is just does not change the image, it just give the same thing. So just simple definition. Uh, as a historical background, the word or an idea just appear in the following papers. Louis, Poincaré, and Picard just mentioned about the fixed point theory. Indeed, Poincaré is approaches a little different topological fixed point theory. The main what can I say, main contribution just comes from the Picard indeed, because Picard just used the so-called method of successive approximation, and that was the what skeleton of the fixed point theory. later I will just say again, but fixed point theory usually just initiated by Stefan Banach. And I will say again, but let me shortly say that in a complete norm spaces, if you have a contraction, you have a fixed point. Actually, what he did, the Banach, what he did, he just go through the Picard idea and he just abstracted what is going on, only the existence of the fixed point. The main idea actually just behind the Picard paper. But it doesn't mean that we should underline or undermine the contribution of the Banach. Banach is successful. Just separate this idea and just improve and consider the other possibilities. So that is the summary of the summary indeed. So that is just to say that why we just like fixed point theory, because we can apply the fixed point theory to several problems, almost all daily life problems can be illustrated. Even just finding zero can be considering as a fixed point theory. Or we can just go to the number theory and existence of the perfect number can be translated into the fixed point theory. And definitely we have a lot of differential equation or ordinary differential equation and integral equation, etc. Several application can be found, but this can be seems a little extreme. So usually we classify the fixed point theory in under these three stream: topological fixed point theory, metric fixed point theory, and discrete fixed point theory. Today I'm mostly talk about, or I focus myself to metric fixed point theory. Uh, for example, this Brouwer fixed point theorem, he say that existence, but he did not talk about the uniqueness. So the metric fixed point theory or Banach stream is very interesting from us for this point. We will talk about the existence and uniqueness. Actually, I will maybe repeat again myself, but Banach contraction principle is very important because we also do not say only the existence. Bro say that there is a fixed point, but he did not show that what is that fixed point or how you can reach the fixed point is unclear, as far as I know. But for the metric fixed point theory, we will just indicate that you can find the fixed point theory just starting to any point and just using the successive approximation, you get the result. Okay? That is the idea. That is why metric fixed point theory take attention to the many authors. I write the every contraction on a complete norm space has a unique fixed point. Uh, but uh, in most of the book, it is written that complete metric spaces. That is why I just write the Italian mathematician Cacciopoli. He used the metric idea. Uh, Banach just restricted himself to the norm spaces. In that moment, the norm space are very interesting. They just focus on the norm spaces. Actually, uh, just three mathematicians, Weiner, Banach, Han, and the Banach just focus on the norm spaces. Actually, Weiner just reached the idea, this norm and complete norm idea, but he just left mathematics and passed to the economy. He is a clever guy. The Banach just now the owner of this idea. Now, Cacciopoli first time say that every contraction on a complete metric space has a unique fixed point. Okay, so that is the idea. So this is the formal contraction definition. This is the contraction. Actually, if k is bigger than that, it is just the Lipschitz condition. And definitely this T, this mapping is continuous, although in any statement we don't use the continuous condition, but implicitly we have a continuity. So what is the idea? T as a fixed point, uniqueness and convergence, as I said, this just comes from this Picard iteration, and this is actually just the successive approximation benefit. I have a small what remark, historical. Uh, by chance, we find this paper of the Gorstadt, and actually, if you just check this statement is exactly actually the contraction of the two variable function. One of them is fixed. And this paper is appear in 1903, before than Bana. But since he used the idea in the solution of the some equation, uh, we or the historically in I guess not many people just mention this contribution. So to be give the honor of the Gorstadt, I just put this slide also. Okay, so it was the French one. This is the translation. If you know the for myself because I don't know the French. Okay. Okay. So that is the first slide that I repeat myself again. So we have a contraction in a complete metric spaces. So we have a unique fixed point. Yes, we have a unique fixed point, but now we just indicate that what is the unique fixed point. We take arbitrary point, use the Picard iteration, and first of all, we get that it is asymptotically regular. So by the continuity of the T, we have already implicitly, we get the uniqueness and convergence of the limit, which is just the fixed point. And by the reductive axiom absurdum, we get the uniqueness from the cases. So, uh, so fixed point or Banach fixed point theorem is very useful in the solution of the daily problems. So we just like this idea because of that we just reach the exact solution. So the exact solution problem can be translated anything. So I just give the two example at the beginning, but this is another example for the Volterra integral. You will just manage the constant k and you get the result. And additionally, you can get some bound, some approximation for the, not the exact one, but for the any n, you get some approximation. This can be also useful in many calculation. So uh, what this idea before, uh, this Banach-Ketchepoli, maybe the correct word is Picard-Banach-Ketchepoli theorem, uh, is the perfect statement, like a poet. Okay, so in the mathematical history, we will just try to find the statement as perfect as possible, as short as possible. We remove the every unnecessary condition. So for this one, that is the cases. To explain that one, we will just talk the other cases. For example, is two example. Okay. So if k is equal to 1, we will just see as from this example, we lose the fixed point theory. So in that cases, T is not contraction, but T is called non-expansive mapping. For the non-expansive mapping, the Banach contraction does not work definitely. Uh, if we have such a strict inequality, it called contractive map. For this case, we have also cannot guarantee the existence of the fixed point under the condition of the Banach, of course. So instead of giving the proof, I will just consider some trivial example graph. Okay, so that is our motivation. Why we like the fixed point theory? Because it is a perfect statement theorem solution for the mathematician. They like to get such a perfect result. But it also give guarantee not only existence but uniqueness, but also it show that how you can get the result, and there is a huge application. That is why we have each year published maybe 100 papers on the fixed point theory result. So after Bana, the we come to this point. So Banach just consider these two distance, okay? The distance of the image and distance of the point. And they just compare that. If they get the inequality, that is called contraction, we say that fixed point, okay? So later, Canan just consider that what happened if we just consider the other distance, this one and this one, instead of the only considering this distance. So he just get a successful result. The constant, since we have a two term now, constant should be 1 over 2, not between 0 and 1, but 0, 1 over 2. The main contribution is not this inequality indeed. Here, the continuity condition dropped automatically. So that is the main contribution of the canon. Okay. So later, it is reasonable, of course. If you look at this part is just the canon type. This is the Banach type. So if we combine this two theorem, you can get another result. Now this constant can be 1 over 3 if the average constant is same, or totally they are 1. Actually, we can just consider for this one also. We can just put one constant here, alpha, beta, and the summation is less than 1 is also possible. Okay. So this result just given by three mathematicians, Rus from Romania, Ciric from Serbia, and Rich from the Israel. So Bianchini, an Italian mathematician, considered the now Canaan type, but instead of the addition operation, he just used the maximum operation. It is also very reasonable. So uh, we have another combination. This order is not true. First of all, we can just consider now the Chatterjee. Chatterjee did it what? This distance, the mixed distance, x and ty, tx and y, and compare with the image distance. So this is the Chatterjee result. And Segal just considered xy like the Ciric, Rus, and Ciric, Rus, and Rich did it. And there are a lot of combination can be considered. Actually, here this is as you see, the old combination. We have a 2-point image of the 2 points. So finally, we have 4 point. From 4 point, we have just actually 6 different distances. So all possible distances considered in here. So that is the first initial linear extension of the fixed point theorems. Okay. So here we have a result. What is that? T is not continuous. Actually, T has a fixed point, but our theorem cannot apply. Instead, here iteration. So the iteration just provide the fixed point. So this idea, this is another example of the iteration provide the fixed point. This idea just uh, going to these results. Ketchapoli theorem, one of them. If you have a iteration, if it satisfies the condition, we have a fixed point. Or another theorem, Kolmogorov. Here we have a iterations, we have a fixed point. In the Kolmogorov theorem, at the beginning, if you just consider the example, T was not continuous. For the Kolmogorov, T just continuous, but later it was understood that this is a superfluous idea, so it was also removed. Uh, Segal considered more interesting result from my side. So for this n is fixed for, I mean that there is a n, but this n is work for every xy. But here it is very pointwise. For each x you have a different n. And still we have a such condition and we have a fixed point. Again, at the very beginning, Segal considered the continuity is necessary, but later Guzman just understood that the continuity condition can be removed. Uh, these are now nonlinear cases. Why I say nonlinear? Because now we put additional auxiliary function like this alpha 0 to 1. But basically, what the role of the alpha, instead of the contraction constant key, we will just have some operator or function just do the similar job. So here, Rakotic use this alpha instead of that one. Boyd and Wong just consider another type, another function, and they use the phi of dxy. You can just think that if it is t, phi of t is equal to kt, just provide the Banach contraction. So, and this idea, this function can be considered with other function. The Browder and the Matkowski, if you look at the statement is same, but the corresponding function are not the same. That is the idea. Mayer-Kaler is completely different approach to the fixed point. So it can be considered as a uniform contraction, something like that. Gerardi gives the like the Rakotic idea, but the condition is different. Uh, Albert and Guerra use another contraction. Now we have a subtraction. We have a subtract from the original one. And then Dutta and Chaudhry consider that if we apply a function to the first part, does it work again? Yes, we have still fixed point theorem. So we have maybe 100 different type of, maybe more, of course more than 100, maybe around 1,000 different type of the contraction. In that point, we will just reconsider that is, are they really original? What I mean original, whether some of them are equivalent to each other. So this is a trend. One of the good results just give the Yansky from the Polish mathematician. He understood that several fixed point theorem are just equivalent to each other. Okay, so this is one of the example. Uh, Actually, Rhodes is one of the also big contributor of the fixed point theory, I can say. He just compared 255 different contractions, and he just tried to understand the relation. We don't have always the equivalence, of course. And this is just the continuation of this work. They will just fill some the blank because he say that I have no idea about this one, and they just give some idea about this one. These are the uh, result in papers. So we have more result about this trend. So what is the idea of this paper? We will just understood that these two results are equivalent or overlapping to each other. So these are the some of the reference about this one. Now, for me, one of the main idea is just to discuss the distances. Okay, so consider the fixed point theory, metric fixed point theory through the distances. I just start or initiate to talk about that one, but let us go further. Okay, mostly we will just use the standard metric fixed point. Standard metric fixed point indeed just the extension of the Euclidean distance. Okay, so you just make the abstract of the again like what Banach did it to Picard. So Freshe just consider that how we can just abstract the distances from this standard measure of the what the length, etc., from the Euclid distance. The result is comes from the Freshe. Freshe use exactly L function, but the name is comes later. Uh, Later say it is called the metric. So we have a four statement, four pillars, we can say. Actually, you can just prove this into statement. It is possible to prove that this fixed point, this metric structure can be observed only two pillar. But what I choose four pillars, I will explain later. So these are just a simple example of the metric. What is the unit ball? So why we have a different standard metric, etc. These are the classical fixed point results. So let me just come up to these cases. Again, if we divide these four conditions, we have a, if it is satisfied, we have a matrix structure. We say that. So why we just divide in four or later five? So these are the standard metric. These are now additional condition. Additional condition, if you look at that, I just mentioned as the 4A, 4B, 4C, etc. Let me just try to say that usually to extend the structure, usually they play with the what? Triangular inequality. Indeed, indeed, yes, indeed. The sum of the idea is very interesting, at least from my side. So if you look at this one, dxx is 0, it seems very stupid axioms, is it? From the mathematical point of view, how can it be different, is it? So my distance to the myself is 0, so it is very clear, yes? So, but for the computer science, life is different. So suppose I just define xy in that way. This is a bare function, it's called. I can define this is in the 1 over 2 to the ds. ds means that the number of the same what component, okay? So definitely in this definition, if you have x times x, so it is 1 over 2 to the power infinity, and that is the 0. Indeed, here, what is the our set? Set is the infinite sequences, set of infinite sequences. So the question comes from the computer science that how we can use the infinite sequences in computer science. If I just put the infinite sequences, how we can terminate that, okay? I have a terminated life or the finite life, so I need to terminate the whatever I programmed that. So they say that we want to consider not only infinite sequences, but also we just add the set of finite sequences. So if it is finite sequences, life is easy because consider now again a distance, but now x is what? X is x1, x13. So in this case, what is the distance? Dxx, definitely not zero. So this is a perfect idea for the computer science. And it is not a metric, definitely. It is a called partial metric spaces. And it is very useful for the computer science, especially in the domain theory problems. Okay? So the others are also very interesting, but this one is very important in dislocated metric spaces and partial metric spaces lose the necessity of the self distances. The others are usually, as I mentioned, that playing with the what triangular inequality, and we have a lot of different type of the distances now and distance structure, and the idea is what in that structure whether the fixed point theory valid or not. Okay, still can we say that they are valid? Okay, how can I do it? I didn't know. No, I don't want to thank you now. I will, but don't worry. Okay. Mm. Should be very kind to this remote control. Yes. Okay. So these are a list, some of the list of the structure of the metric, and these are other type of the metric. So these are very original, and there is no equivalence, of course, about this structure. But this is another story. I just need to maybe mention a few minutes. So this is the mathematician do it. Okay. Up to now, we just play with the axioms, okay? So these four axioms, and we get result. So in this table, what we change is the image, okay? So we do not use the positive half line, but instead of, we just use the sent it to the what Banach spaces, or as it said that complex spaces, or quaternion spaces. Do we have another thing? C algebra valued spaces, and so on. So what is it? Very interesting because in the real life, we know, we have an experience, we know what is the bigger, less than equal, or greater equal. For that one, we just need the positive cons. We have a cons. We need a con, positive con. So if you just consider the positive cons, you get the, for each one, we have a different con, of course. We get the inequalities, and we can satisfy the condition. But the satisfying condition, especially for these ones, are very artificial. I did not put to slide the details, but it is very artificial. So what is the idea about this one? This is at the beginning very interesting. Maybe for the application still interesting, but it is for us, I can say that something like that. For us, it is not very important because if we just use the scalarization function, you can just get that maybe this is D, usually this is D con. So D is equal to D con composition, this function, or function this composition, this one. You get easily get the same idea. So for at least for the fixed point researcher, these construction are not very interesting. Yes, this is another what trend. I can explain easily because in my first draft we will just say that we have a 2 point and image of 2 point. They say that what happened if we just consider the 3 point, an image of the 3 points. So instead of the line distance, they will just, one of them just consider perimeter, one of them just consider the area of the triangular. We have a 3 point. So we have an area or perimeter of the triangular. So they just construct the structure and get such a different kind of the metrics. But unfortunately, they do not satisfy very interesting results somehow the standard metric spaces. So it was proved that almost all of them are equivalent to each other. So I can stop here. I can actually talk more, but let it me just stop here, I guess. I have. Thank you.
Thank you very much for this night talk. Any question or comment, please? Yes.
Okay, then the following question, that you showed us so many theorems on fixed points, and now the generalizations of the metrics. So is there also a theory of fixed points with all this like system algebra valued metrics? Does it make sense at all? It's a very naive question.
Maybe for the application part, they can see that maybe we just use this result in that structure easily and use this point in that structure, get the advantage. But for me, it is not, because I can just get the same thing easily. For me, it is also easy. So because I write almost all different kind of remark papers on that one, and later they will just say that, but you are right, but in application this can be good. Okay, what can I say to them? But in mathematical sense, in function analysis, I don't see that this is interesting for the mathematician they create for me a trash, because a lot of the reputation of the same thing for the same part. Okay, what can I do?
For the first part of your talk, what happens if the contraction property is only in a ball, not in all the space? The contraction property.
There is two type of the fixed point theory, if I understood you correctly. One of them is the general, one of them is the local contraction. They are also worked, but local contraction almost easy after getting the general part. But again, it is interesting for the who work the problem because the structure can be very big, but you don't need to satisfy all structure. You can use only some local parts. That is possible. I don't have a problem about that one. No, it's mine.
Any question? More question? No. We thanks again the speaker. Our next speaker is Professor Elena Bendisheva. Her research focuses on harmonic analysis, approximation theory, and extremal problems. He's come from University of Cape Town. And the talk is duality or a type of extremal problems or locally compact abelian groups. Okay. Take your time.
Thank you very much. Next moment. Excuse me, can you please start the new slides? Thank you. Okay, let's start. Thank you so much for the introduction, putting my slides on. As everyone, I start with thanking the organizers by bringing us here, inviting me. It's a beautiful place, great people, very good mathematics. Like it very much. So it's a result of a joint work with this set of people, Balen Farkosh, Marcel Gall, Mita Ramabulano, who is here, and Sila Trivius. What do I do wrong? Oh, I think I did something wrong. You know what?
It's not related with that one. No. Not related. They will open.
They will open. So, but these are the two, yeah? These are the two.
This is and this one.
Ah,
Back forward.
back forward.
Yes.
Okay, so this is for.
Forward.
Thank you so much. Yeah. Okay, sorry. Yeah, was. Huh? No. Yeah. Oh, yeah, I see now. Yeah. So it just took time. Okay, but nevertheless, okay, now let's start. See? It will be about positive definite functions. See, we already saw them yesterday in the talk by George. I start with this first sentence, which impressed me so much. It this quotation from Berends, who was my postdoc advisor, positive definite functions, inexhaustible topic. A definition which we already saw yesterday, function is called positive definite if this is true. Yeah? So basically for any choice of points, the matrix built of phi of xn minus xm is always positive for non-negative definite. Okay. Oh no, it really doesn't work. I don't know what I'm doing. Oh. Ah, yeah, sorry. Towards the computer. Thank you. Yeah. Yeah, but we now go back all the way back. Uh, okay, thank you. Okay, simple properties of positive definite functions. They were already here yesterday. Okay, maybe you just read it. An important example of a positive definite function is what we call self-convolution. I take a function phi and then I take a little bit of modification. If phi is real, then it's necessarily even then it's really the same as phi, and then we convolve it to itself. So this is a construction that always works. Aha. Bochner's theorem was written down in the exact form yesterday. Well, roughly speaking, positive definite functions are functions exactly with the non-negative Fourier transform. I'm so sorry. Okay. I shouldn't definition on RD, but it need not be RD. It can be done exactly the same way on locally compact groups. Positive definite functions play many roles. We saw yesterday a very interesting talk by Church about completely different things. I'm going to go into the direction where positive definite functions help us to get estimates for certain geometric problems. And what will now follow in the next 2-3 slides is shortened version of what I showed last year in Porto at the conference. So there is some intersection in the public. You will maybe recognize it, but then we will do other things. A very famous geometric problem is sphere parking. The idea is that we put solid spheres of the same radius in the space, and we want to have the densest parking. Yeah? So you want, like this hall, you want to put spheres there so that as many as possible are coming inside. Oh, how I'm unable to work with it, obviously. I'm very sorry. Okay, it's a very classical problem. Here are solutions in the dimension 2 and 3. In 2 is honeycomb, is 3. The idea is that you take the solution in 2 and place layers so that the next layer, the balls go into the holes of the previous layer, but you can put it like this or like this. So there are some small variants. This is one of them. It's interesting that the solution of the dimension 3, the full solution is very recent. Yeah? The problem, it was already conjectured by Kepler. In Middle Ages, the full solution arrived only in the 21st century. And, oh. Okay, And there is a famous result, famous approach by Marina Wizowska, who got Fields Medal for these results. These are dimensions 8 and 24. It was actually before the dimension 3. And well, no further results known. Another problem, which is maybe a little bit less famous, but also relatively well known, is the Kissing number. Now, again, placing spheres in the space, but now the question is different. We fix one sphere, and then we put spheres of the same radius around so that they touch. They touch, but they cannot intersect. The question is how many spheres you can put. So it's a different problem, similar but different. It's so-called Kissing number. Okay, so how to solve such problems? So typically there is a candidate. So especially with this sphere problems, y dimension 8, y dimension 24, because in these dimensions there were candidates, there were packets. Everyone believed that this is the solution. But how do you prove that you cannot do better? Yeah, this is the question. And you cannot do it within geometry. No? So you need an estimate. You need an estimate that says you how well you can actually be. And this is one of the approaches there is indeed to use harmonic analysis for positive definite functions. And what Marina Wizowska did in particular, that she solved the corresponding variant for the dimensions which gave her solutions. And the problem she solved is the Delsart problem, which was already known to the community from the work of Delsart. This is the problem. Let omega be a closed convex central symmetric set that contains the neighborhood of the origin. For problems with spheres, it's a sphere, but you can also put it more general. And we consider the set of real valued continuous functions phi such that they are positive definite, they are normalized at the origin by the value 1, and they are non-positive outside of our body. Yeah? So for the sphere pocket would be non-positive outside of the sphere, and the question is how large the integrals of such functions could be. And well, I'm not showing the details, but this gives you an estimate on the pocket density, for example. This idea to use this type of questions in harmonic analysis for geometric problems come back to Delsart, 72, who first used a very similar approach, but in a bit different situation, and it was not in terms of the Fourier transform, but in terms of Kravchuk polynomials. So Fourier transform in terms of Kravchuk polynomials to solve some problems in the coding theory. Not many solutions are known at all. This is some selection of people who worked on it, and dot 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 stays for all people who are not mentioned here. So like every case is practically a solution made by hand. So there is no general approach. Very close relative is the problem which appeared partially under the name Turan's problem. It's exactly the same up to the condition 3. The condition 3 is different. So in the Delsart problem, we expected from the function phi to be non-positive outside the body. Here it must vanish outside of the body. Strictly 0, the same question. Okay, again, a selection of names who worked on it, and you see it starts much earlier. Yeah? So Turan is already somewhere in the second part of the first line. Again, dot, dot, dots for many more names. Solutions are only known in a very small number of cases. And, so for convex bodies, all the solutions are Euclidean balls. And okay, in their transformations, you can apply a linear transformation here. And tiles, which are the same as spectral sets, tiles are bodies such that you can fill the space with translated copies of them. Or actually different sets, different sets of tiles. It's a little bit more, but well, roughly speaking, this is it. Okay, the first name in the previous slide in the list of names was Ziegel. And it was a discovery for us made by Szilárd Revius. After we already worked on this stuff for several years, he discovered that paper. And turned out that Ziegel already formulated and solved the problem as early as 1935. And he actually seems to be the first who came to the idea to apply the problems for positive definite functions to get estimates for geometric problems. And the problem he was approaching was that he wanted to give a second proof, an independent proof of Minkowski lattice point theorem, which is the following problem, purely geometric problem. We take omega to be a closed convex centrally symmetric set. And then we look at the points in the space with all integer coordinates. Okay, 0 is of course there in the body, yeah, because it's centrally symmetric, but now we want that no other points with integer coordinates are in the interior. How large the volume of this body can be? The answer is 2 to D. And it's a sharp estimate. An example is very simple, it's just a cube which goes to points like let's imagine a square. Yeah? So 0, the region is allowed to be there, all other points can be only on the boundary. How big the body can be, well, this is obviously the biggest what you can do. Yeah? This. Hmm? Oh, it doesn't matter. Yeah, open then. Yeah, doesn't matter. But I'm trying to say that it's not trivial. This answer is not absolutely evident, because what if I maybe can put something like this, like something like this, which avoids all the points. Maybe I can put some body which is narrow but is very, very long, and then I get a bigger volume. No, I cannot. This is the aim. And this is seems to be the first person who started to work with positive definite functions. And then after that, it turned out that the Desart formulation, where the functions are not vanishing but can be also negative, is more effective, gets better estimates. Aha. We do it on locally compact abelian groups. Okay, set of notations. G will be a locally compact abelian group. Lambda G is the Haar measure. I'm sorry. Aha. Okay. Now I'm going to work with two sets, not just one set, but two sets. It's generalization omega plus and omega minus. Omega plus is supposed to be a neighborhood of 0. And we consider the following class of functions. So as you see, it's a straightforward generalization. So functions are positive definite, normalized by the value 1 at the origin. And the entire place where they may take positive values is inside of omega plus. Yeah? So all positive values are inside of omega plus. All negative values are inside of omega minus. And the assumption that 0 is in the interior of omega plus is natural because of this inequality. Yeah? So if 0 is not in the interior, then my functions all are identically 0. So the class is empty. Aha. And the problem, the extremal value we are studying is exactly the same to maximize the integral. I'm so sorry, I don't know what to do. Seem to be unable to work with it. Well, here we are. Our Turan problem and Delsart problem are particular cases. For the Delsart problem, we took omega minus Bg, so negativity is available everywhere. And for the Turan problem, the positive part and the negative part should be all on omega. Then the function is 0 outside of omega. Okay. Well, we studied them, different aspects of them. Now, what is going to be the topic of the talk for the remaining part is the duality. So these are linear problems, linear extremal problems. So they can be considered as problems of infinite dimensional linear programming. So one of the typical things what people do in linear programming, ask for duals and ask for the duality statement. There is some prehistory in some more or less more specific situation. There is a result of Imre Ruja on the discrete group Z. Actually, it was Z and Szilárd Révős. Oh, I forgot the name. The year 91 on ZD. In connection with some questions of in number theory. Finite abelian groups, Mathematology and Imre Ruja. In the continuous case, there is a very important paper, important for us, by Aristov and Babenko, where they studied the Delsart problem, but not in terms of the Fourier transform, but in terms of Gegenbauer polynomials. So again, Fourier Gegenbauer series, and on an interval, on a compact interval, and they formulated a dual problem. They proved the strong duality statement, which means that the values of the primal problem and of the dual problem coincide, and they did it in connection with the Kissing numbers in the dimension 4. So this big, again, there was a candidate, and the big hope was to prove that that candidate is optimal. But they arrived at the situation where they cannot prove it. So they still had two possible values. There were still two possible values. Kissing number is a discrete number, yeah. So it's a number of spheres. So it's a integer, and they still couldn't exclude one of the values. So there were still two values, and for quite a long time, their work was the best in the dimension 4. But then, like maybe 10 years later, Oleg Musin came and actually closed the case, excluded one of the values. And historically, I must say that Vitaly Aristov was my PhD advisor, and Alexander Babenko was his first PhD student, so to say my brother in PhD. So this is where I come from. Okay, on RD, it took much longer because this is a non-compact group. So it's neither discrete nor compact, so things are more complicated. Kohn and Elkins formulated 2003 the dual problem, but they didn't prove any strong duality. There was only weak duality. And then there are more recent results, as you see, where strong duality statements were proved on RD. For the Turan problem on RD, there is a paper by Gabardo, 2024, where he also worked with strong duality, and at least for the balls on RD, he could prove strong duality statement. But all these results mentioned here are really RD specific. They use some specific features that are only available on RD. And what we want to extend it to the abstract setting, yeah, not to use any specific structure of RD. And yeah, we managed to at least get some results, not yet at the situation where we could cover everything what we want. And on locally compact abelian groups, and part of our results actually is even extended to Gelfand pairs, and this will be the talk by Mida, subsequent talk today, later in the second part of the meeting. And there are two papers written parallel, and both are available on arXiv, not published yet. And in one paper, we exactly followed the approach from the paper of Aristov-Babenko, extended it. And in particular, extended it from the Delsart problem to this more general problem with two restrictions on the set of positivity and on the set of negativity. And there is a second paper which is only for the Delsart problem, but on locally compact abelian groups away from compactness. And also the goal functional is more general. So we're not just maximizing the integral with respect to Haar measure, but more general, practically arbitrary functional, and also the normalization, which is here just delta function applied at 0, is also generalized to, well, almost arbitrary functions, so there must be some natural assumptions which you cannot avoid. I'm going to concentrate on the first paper. Let me please check the time. Okay. As I told you, the first thing we started with, we studied the paper by Aristov-Babenko, and they used the theory of duality in infinite dimensional linear programming, which we are going to use too. And this theory goes back to Duffin. There is a paper from 1956. It can be, so for linear programming, it can be, however, and this was generalized to much more general setup. It's not linear programming, but in particular, convex programming and even more. And so the name's also relevant for us. There is a big paper by Ofer Tikhomirov, and there is a series of publications by Goldstein, and these were our sources. And now I'm just going to shortly present the theory following Duffin, but with our terminology. So each of the people use his own terminology. So we found some way, also our own terminology. Let E be a real linear space with a locally convex topology, and then we take its topological dual. So I'm going to have P and topological dual. Okay, the action of X in E star on Y is denoted by this. And we select an E an arbitrary closed convex cone, which we denote by P and call it a positivity cone. Okay. With the help of a cone, we can determine a pre-order on E. So we say that Y1 is greater equal Y2 if the difference between them is in P. Therefore, the usual positivity on R, you will take as a positive on the positive semi-axis. But it can be done also in the abstract setting. Aha. Okay. A positive cone on one of the spaces C induce the dual cone on the dual space P star. And this is defined in the following way. So I thought those functionals such that their value on all non-negative elements is also non-negative. And then we take P star for the positive cone in the second space, again with a pre-order. We need the second pair. We need the second pair, F and F star. Let me, for a reason, write it like this, F star. And also there we take positive cone Q and its dual Q star. And now I consider linear operator T from E to F. A linear programming problem we consider is formulated the following way. I have a goal functional. So the goal functional is, so X is living in X star, so X is living here. The goal functional is determined by an element C here. And then I have restrictions. So X must be non-negative in the corresponding positive cone. And the second restriction is that Tx must be greater or equal B, a given number in the space here. So it fully corresponds the case on RD, where T would be just a matrix and all spaces are spaces Rn, Rm. An element X star is called feasible if it satisfies the assumptions. A problem calls consistence if there is at least one feasible element. If there are feasible elements, then naturally we can define the value of infim. It can be also minus infinity. This is not excluded. And in this case, U, this infimum is called the value of the program. I don't know what to do. Just really just press once and it brings me all the way back. I'm so sorry. I don't know. It just does it on its own. Oh, okay. Here we are. I'm absolutely sorry. Okay. Notice that an element is feasible if, well, the first condition, the non-negativity remains the same, but the second condition can be written like this: Tx is B plus Q, where Q is non-negative. This will give me exactly the estimate. And so, looking motivated by this, Daphne introduce the following thing. Okay, let's look at the problem where we don't require that the second condition is actually fulfilled. Let's just look at the sequences where this condition is asymptotically fulfilled. So now we relax the condition. So the condition was once again Tx greater or equal B. We relax it. We consider sequences and only want to have it asymptotic. So now Txn is B plus Qn, where Qn is non-negative, plus some error Zn, yeah, which can be actually negative. But Zn goes to 0. So it allows us to look at the points where they are not strictly speaking feasible, but they are asymptotically feasible. Sequences which are asymptotically feasible. So such sequences are called asymptotically feasible, or we call them asymptotically feasible. The problem is called asymptotically consistent if they exist asymptotically feasible sequences, and in this case, the corresponding value of the infimum is called the asymptotic value of the problem. So it's a relaxation of the problem. Okay, it is very easy to see since when we took these asymptotic sequences, we enlarged the set and we're looking for the infimum. It's absolutely straightforward to see that we always have the inequality that the asymptotic value is less equal than the actual value. And the problem is called if possible, if they ill-posed, if they coincide. Okay. And now I'm going to formulate the dual problem. So this is just a formulation like in linear programming, in classical linear programming. I look at the second operator. The second operator, which is called T star, is the dual operator. It works like this. In Duffin's approach, we require, however, a little bit more than just the existence, because the adjoint operator typically would be the operator not in E, but in E star star. Yeah, so it's a second dual space, and if the space is reflexive, they coincide. If they are not, if the space is not reflexive, it's a larger space. And we here actually want that T star is existing, the T star exists, and it actually maps back to E. A non-trivial condition, but it will be fulfilled in our applications. Okay, and now I can formulate a dual problem. So now everyone who is familiar with finite dimensional linear programming will immediately recognize this. So the left problem is the primal problem, the right is the dual problem. This is a typical formulation. No. Am I lucky not? Okay, yes. The big question in the duality is to establish the so-called strong duality. So I have two problems, the primal problem and the dual problem. They are connected to each other formally, but what about the values? The strong duality theorem is that the values coincide. This is the goal. It doesn't work always. You need some conditions. And this was a genius idea of Duffin, that instead of looking at the primal problem U, we look at the extended problem and the asymptotic problem UA. It seems that he was the first who introduced this idea, and this is the theorem. A problem of linear programming is asymptotically consistent and has a finite asymptotic value if and only if the dual problem is consistent and has a finite value, then the values coincide. So the value, basically no assumptions. For the operator T, we only request linearity, not even continuity. And we have this duality statement, just not for the original problem, but for the extended problem. But we introduced the well-posedness. The well-posedness means that you and you are the same. Yeah, so then in this case, we have a strong duality statement. Okay, what are we doing? In our case, we have our compact abelian groups. So now the result is for the compact case, compact abelian group. G by gamma, I denote the dual group in terms of Fourier analysis. So now it's completely different duality. This is the group of all characters, which are continuous homomorphism of G to the multiplicative unit circle. Okay, I will not try to that. Okay, for the first space E, here I take L infinity on gamma. But now L infinity is here, it is pre-dual, yeah, I need to have a dual space here. And noting that L infinity is the topological dual L1, And we're exactly in the situation where we don't have reflexivity, so one should be careful. Uh, then we take E with the weak star topology, and it makes it linear space with locally convex topology, and then the topological dual will be exactly L infinity. So I have now pair L1 and infinity. And the bilinear form is here the usual bilinear form. For the positive cones, we take very natural choice. These are non-negative elements in these spaces. Okay, what is the second pair? The second pair is much more complicated. As F, we take the space of continuous functions on G with the norm topology. F star is in this case the space of regular signed Borel measures on G. G is compact, so we have these representations. But what is now the positive cone? So remember, we have functions that must be positive. They're allowed to be positive only inside omega plus, and they're allowed to be negative only inside of omega minus. And so for the positive cone here, I take an intersection of the two cones. This is the cone where functions are all non-positive outside of omega plus, and this is the cone of functions which are non-negative outside of omega minus. We need both, so we have an intersection. What is then the dual cone? It's highly non-trivial. You can write down easily a dual cone for one cone, but we have intersections of two cones. This is a quite non-trivial thing, and this is our first statement, is that we determine the dual cone of Q, which is the following. So I determine the dual cones of the individual cones, and these are non-negative measures that are supported only outside of the body we have. And the non-trivial fact is that the dual cone is exactly equal to the sum of these cones. The general theory gives you that it's a closure of the sum, but we can get rid of closure. And once again, back to the problem we consider. This is the function class we consider. What I did now, I removed here the normalization and replaced it just by the condition that phi is not identically 0. F will be a Fourier transform of phi, which is a non-negative summable function. Notice that the functions of this class are exactly functions that allow representations of this form. So there's a Fourier series, gamma is the character, F is Fourier transform in this case, such that we have our condition on this side. Okay. And from this point, we more or less follow the approach of Aristov, Babenkov, Revine. This is the constant we investigate here. So I just put the normalization here. And in terms of the Fourier transform, it can be rewritten like this. F is the, what is this check, is the inverse Fourier transform. And we want to take the supremum of it, and it's the same as to minimize the sum here, yeah, the sum here. So we consider equivalent problem, which is the minimization problem. So we minimize the sum of f of gamma for all gamma except for the 0 on our class of functions. And they are obviously connected by this simple equation. Let me please check the time, because I'm of course losing time. Oh, I'm afraid I have only 3 minutes before I must finish. Okay, so this is now the problem U, the problem of linear programming we consider. So we can just determine explicitly the adjoint operator which satisfies our conditions. And then we can just formulate, take the theory, write down formally the dual problem, which is like this. And for the dual problem, I have a more intuitive representation. When I write down everything which is here, we take the supremum of minus mu of G, but this is non-negative number. Mu is negative, such that mu is in the con Q star, and we have these restrictions here. Nah, please work. Okay, our aim is a strong duality, and for that we need to show that the problem U is well posed. Okay. Consistency is very easy to see in this case. The non-trivial fact is to show that it's well posed. For that, we consider the extended problems. So now, when I am having the sign condition, so let's say it's my omega plus, omega minus. So the function can be negative here, cannot be positive, must be positive here, and must be negative here, but we allow a little bit tolerance. So this function can be actually negative, but bounded by epsilon. Yeah, so within this epsilon. And then we want to show, of course, that the limit when epsilon goes to 0 is this. So I need to finish. I hope that please work. Okay. If it's a Delsart problem, this means that there is no actually second restriction. So we have only one side restriction. It can be done by repeating the argument. Ugh, please. Okay, repeating the simple argument by Aristov Babenko, it's quite easy to see that if f is feasible in the original problem, that 1 minus epsilon f is feasible in the extended problem, and then epsilon goes to 0, the values are coinciding. Okay, the situation is much more complicated if we have two-sided conditions. That's why the second paper is only for the Delsart problem. It's much more complicated. This approach doesn't work anymore. But we were lucky that we had an idea which we could grab and use from Mita's PhD. It could be adapted and used in our situation under some relatively natural topological condition. I don't have time to say we were able to look at the compact case, at now general subsets, two-sided problem, and formulate the strong duality condition. And now let me just translate it back to the original problem. What is then the dual problem of the original problem? We need one more definition. T0 of G will be a subset of measures that are positive definite, and the total measure of the group G is 0. And this is the main result here. Let G be a compact abelian group, omega plus, omega minus, Borel subset, satisfying. Then the linear programming problem, exactly our program, has this dual problem. So it's the infimum of values alpha, such that alpha delta 0 minus Lebesgue measure are in this cone. So this first part is exactly Q dual, and then we have a small correction term here. And moreover, we have a strong duality statement here. This delta 0 comes from the normalization. The functional normalization is exactly the value of the origin. Lambda G comes from the goal functionally integral with respect to this measure. Yeah, this is it. Okay, so basically this is the end of the talk. Let me just go through. For the Delsart problem, we can remove this topological assumption. No, please work. Okay, we can generalize the normalization by a more general functional, not going to go into that. Okay, and this is my literally last slide. There will be a subsequent talk after the coffee break where Mita will continue where I stopped and discuss the case of compact Gelfand PS. Thank you very much for your attention. I'm extremely sorry I somehow didn't manage to work with this. Thank you. Thank you.
Thank you very much. Do you have any question or comments? Yes.
Hi, thank you. I have two naive questions. One is, in the cases you described where E and F were continuous functions or They're not reflexive. Are there situations when E and F are reflexive? Are there natural situations? So then you don't have the problem about the bidual.
I'm not, yeah, thank you for the question. I'm not sure I understood the problem. Well, continuous makes sense because if you allow discontinuous functions, the entire theory breaks. Yeah, I can have a function which is just zero everywhere, one at one point. It's positive definite function, doesn't bring me anything. So continuity is a very, very natural. But then you're already out of reflexivity. Yeah? When you take C, you're already out of reflexivity. On the other hand, we maximize the integral. So our functions must be integrable. The Fourier transforms of positive definite integrable functions are integrable, so you're naturally in L1. Again, no reflexivity. Yeah, so it cannot. So I'm not aware of ways to approach it where you can still keep reflexivity. It's somehow by the nature of the problem.
Okay. Sorry, one other naive question. The first part of the talk was about sphere packing, or had to do with sphere packing. And in other words, it was related to the Euclidean ball. And what about other norms? What about other norms?
Well, yeah, thank you. Well, spherical packing is just an extremely famous problem. That's why I put it here. And as I told you, this is exactly this. There's a problem. Exactly this, one to one. Yeah? Well, I mean, cubes. We all know the solution, right? Yeah. Well, but there are, of course, some more general questions, not necessarily in the space RD, but you can look at, for example, pack the area of the sphere by spherical cups. Yeah. Look at some further spaces. Smith, I will touch this. So some hyperbolic spaces. Then it's already not a case of abelian groups. Yeah, but the packing, of course, can be considered much more general. Yeah. Thank you.
Any more? Yes.
So again, with this sphere packing and this, because first you gave us the definition of a positive definite function, and then for me it was mysterious. How can you tell us more how this relates to? I mean, so the definition is okay, you grasp it, but then all of a sudden you see something. It's like a mystery for me. How?
Well, your question is probably about this magic that happens. Yeah, how comes we have this particular geometric problem? How comes that it plays a role? I unfortunately don't have in this talk. I actually deleted these slides. Probably the easiest way to show would be to show how Ziegel proved the Minkowski help me, lattice point theorem. And the key here is the Poisson summation formula. Yeah, the Poisson summation formula, which says me that the sum of functions at certain values is exactly the same as the sum of, phi, Fourier transforms on some other values. Yeah? And this is how it translates. So if I look at the function, let's say Minkowski theorem, yeah? Or spherical function which lives only on my body, and then I shift it around, but then I can control it by looking at the Fourier transform. So this is somewhere the place when some magic happens, and I don't know, you probably agree with me, I can't tell you really what happens there. So for me, it's still something, just wow. Yeah. But this is the connection between the two sides.
Yeah, on the one hand, with the Poisson summation formula, the um, constant coefficient will spit out the integral, right? On the other side, the terms will vanish because of this condition. So you get an estimate from there. But another way of seeing it is that for the packing problem, at least, instead of packing the spheres themselves, you pack these positive definite functions. So you replace the balls by positive definite functions that decay outside the sphere, and you simply replace the volume of each of these balls by the integral. So this is one way that you can see. Yeah. Yeah. Yeah, it will tell you about the packing because it vanishes when it gets close to other points. And so the integral will control the density. Yeah.
Okay, we thanks again the speaker. Thank you. Finally, it's my pleasure to welcome Professor Juan Gabriel Calvo Alpizar from University of Costa Rica. His research includes PDEs, numerical analysis, optimization, and mathematical modeling. This is not the talk. Well, the title of the talk is Domain Decomposition Method for Irregular Subdomains and Discontinuous Coefficients. Tienes que picar. Si le mantienes. Este es el de adelante y este el de atrás.
So, good morning, everybody. Thank you for the invitation to the organizers in this lovely city. It's a pleasure for me to be here. I'm going to talk a little bit about domain decomposition methods. Um, this is like a family of methods that are used to solve partial differential equations, okay? So my main interest basically is numerical analysis applied to PDEs, okay? So the first half of the talk, okay, I think now I'm understanding the problem. um, okay. So the first half of the talk is going to be a little bit about trying to motivate what we do. And at the end, I'm going to talk more specifically about the problems that I've been solving and working on. Okay. So for simplicity, just consider like maybe the easiest elliptic PDE, divergence of gradient of view, Poisson equation. I'm going to talk about this problem in 2 dimensions, but everything can be generalized to 3 dimensions with no problem. And again, for simplicity, we include homogeneous Dirichlet boundary conditions, okay? So I guess it is well known, you multiply by a test function, you integrate by parts, and you end up with this continuous problem. You want to find a function u in the sublevel space H01 that satisfies this condition, okay? Here I'm going to eventually talk about what happens when the coefficient kappa has high contrast, meaning that it has like high values over the whole domain. Okay, so what you do, well, when you discretize, essentially you replace this sublevel space, H01, by some finite dimensional space. Imagine your 2D domain, the square, then you partition the square. Usually you use, well, we use finite element methods, which are quite well known in this area. So what you do is that you replace your sublevel space by some finite dimensional space. In this case, what finite element method does, in the simplest case, is to use piecewise continuous linear functions. Okay? So this is a typical basis function. This is the canonical basis. For each node of your mesh, what you do is that you take a function that takes a value 1 and is 0 everywhere else, and then you have these kind of hats, and these are like the basis functions that will generate your solution. Okay? And then you replace the continuous problem that I mentioned here before, this bilinear form, instead of testing for functions in the sublevel space, then what you do is that you test with functions in in this finite element space. I'm going to talk now about finite elements. There's been like a 13 years old generalization that is called virtual element methods. Essentially, what you do is you can apply this method to any partition. For instance, I'm showing here an hexagonal mesh. Somehow, what you do is you extend these spaces of finite, of linear, piecewise linear functions. And again, you end up with some bilinear form that I will introduce in a couple of slides. So what I'm trying to say here is that you can work in general polygonal or polyhedral meshes in 2 and 3D. Good. So what you do? Okay, first of all, this is like basic. The first, I think, 3 papers on these topics on virtual element methods by Italian researchers, essentially Beirao da Veiga, Brezzi, and collaborators. And as I said, this is like 13 years old. So what you do, instead of using these piecewise linear functions on a triangular mesh, well, you define these spaces. Again, this is the lowest order case. You can use quadratic, cubic polynomials, or whatever. In this case, you have this first space, V1, which essentially are piecewise linear functions on the boundary of the elements. When I say element, I mean any of these polygons that you have in the mesh. And then in the interior, what you do is that you define this local virtual space, V1, which are functions that are continuous, piecewise, linear in the boundary, and they are harmonic in the interior. Okay. So essentially, what you need to define one function is only the values of the vertices of the polygon. Once you know the values of the polygon, then you can interpolate on the boundary, and then you can solve a PDE to obtain the values in the interior. Okay. This method is called virtual because you essentially never compute these functions. You only know they exist, and that's all you do. Okay? By knowing only the values on the vertices, you can do all the computations that you require to solve the PDE. Okay, so there's a small difference regarding finite elements, if you know that. In finite elements, you solve, you integrate the initial linear form, the uh, product of the gradients of functions. Since these functions are virtual, and as I just said, you don't compute these functions, then what you do is you need to project these functions over polynomial spaces. So, for instance, I will define the projection in the next slide. So what you do is you replace, instead of having here just the gradient of u, you have the gradient of a projection. And since you are approximating your original bilinear form, then you need to add this sum, which is a stabilizing term that takes care of the difference between the function and the projection, basically. So at the end, you have this bilinear form where the, I'm sorry, I forget, is this direction? Okay, in that bilinear form, you have this projection. The projection essentially is a L2 projection of the gradient of the function. Since you are projecting the gradient, you need one extra condition, which is this one here. The average of the function of the virtual function is the same as the average of the projection. And since you only know the values on the vertices, then that's what you do. Okay? So eventually you end up with a linear system. Why? Because, well, you have this finite dimensional virtual space, then you test your bilinear form with all the functions there, and you rewrite your problem as u equals v. Here, what is important again is that this matrix A has the bilinear form evaluated all the basis functions. The right-hand side is just integration, and you can estimate the error and do many things about this. Okay? I'm not going to focus on the implementation or what it means. Here, the important thing is that you have these spaces on polygonal meshes. You end up with a linear system, and then what I'm going to focus on is how do we solve this linear system. Okay? Okay. So again, just to try to motivate a little bit, this basically is a very large system. If you do three-dimensional problems, then you will have a lot of nodes in your triangulation. Why not just invert the matrix A? Well, if you use direct methods, they are quite expensive. Even though if you do some improvements that there exist, you can lose the sparsity of the matrix. This matrix is sparse in the sense that if you have two elements that do not intersect, then the entry in the matrix will be zero because they have no intersection of the compact supports. And therefore, what you do is you try to use iterative methods, okay? And therefore, what you will try to do is, well, create a sequence of vectors that will converge to the solution. And this matrix is definite positive, symmetric. So these methods are based on finding the minimum of this quadratic function. Okay? So these are, I guess, well-known methods, gradient methods. In particular, like the first family of the easiest family is called gradient descent methods. Essentially, you follow the steepest slope. What I'm going to use later is the so-called conjugate gradient, where essentially you compute, if your matrix has size n, then you compute n orthogonal directions with respect to the bilinear form that you are considering. So you know that in exact arithmetic, you will get the solution of your system in n steps. But of course, if I'm talking that we have millions of degrees of freedom, we want to solve this linear system in just 20 iterations or 5 or so. Okay? Depending on the method, you can do that. So I think that's the most important part of that motivates what I do. When you use conjugate gradient, the bound for the error in the step k is bounded by the condition number of the matrix, which is the largest eigenvalue of the matrix divided by the smallest one. So you observe really slow convergence if the condition number is too large. and then what you do is you precondition. And what is preconditioning? You will define a new operator M that has two requirements. First, has to approximate the matrix, because we want to invert the original matrix. And also the inverse of this operator applied to a vector is cheap to compute. And why is that? Well, okay, because essentially this is the algorithm. I'm not going into a lot of details. What is important here is that you iterate, and all you need to do at each step is to compute a matrix product, A times a vector, and then apply the preconditioner M inverse. So you never compute this preconditioner. You don't need to spend a lot of memory on that. You just need the action for one vector. And the idea that you will accelerate convergence. If there's no preconditioner, you have some behavior like the red line. When you precondition, you want the error of the residual to go as zero as fast as possible. And in order to do that, you need to try to get bounds for the condition number of the preconditioned system. Okay, so that's, let's see. Okay, so I hope that's what motivates this area of numerical analysis, which is called domain decomposition. Okay, so the core idea is, okay, if you have this big problem, which will take a lot of time to solve, then why don't you split the problem in your domain omega into smaller problems, into subdomains that we call usually omega 1, omega 2, and so on. Okay? There are like two flavors of domain decomposition. Here I just mentioned the first one. You can create iterative solvers for PDEs, meaning that you can solve PDEs. Okay, I'm going to repeat that. If you know how to solve a PDE in a circle and you know how to solve a PDE in a square, then you can iterate to get a solution in the union of these two sets, essentially. But again, I'm going to spend my time in the second approach, which is the construction of these preconditioners, again, in order to get faster convergence of the methods. So here, I'm just repeating what I said. So we discretize the PDE, minus Laplacian of u equal to f. We get the linear system with a lot of degrees of freedom. We're going to use this conjugate gradient method with preconditioners. And here are some methods. Decomposition literature, there are several methods: additive, multiplicatives, balancing domain decomposition by constraints, FTDP, and so on. Since maybe this is the first time that many hear about domain decomposition, I'm going to talk about the easiest one, which is the additive version. Okay, and keep in mind that again, what we want is that the condition number of the new of this new matrix is much smaller than the original matrix, so we can accelerate convergence in the method. Okay. So the easiest way to do that, okay, is imagine I'm going to use. So the easiest idea is, okay, well, you have your domain. It doesn't have to be that good, but then you divide it and you create what we call overlapping subdomains. So you cover this with several subdomains. Okay. And then the idea is, instead of solving the problem in the whole domain, you solve you solve these smaller problems. Okay? For each subdomain, you need to define a restriction, which is straightforward, because then what you have here is a lot of nodes of your triangulation. Okay, so these restriction operators, essentially what they do is they select the values that you have inside each subdomain. And then with that in mind, you can define this local matrices AI with this form. Okay, Ri is the restriction that transposes the natural extension by zero to the rest of the domain. And then you can define what is called the one-level additive sharp preconditioners. Okay, they have this form. It's like a sum. Essentially, if you think this in the matrix form, what you have is you have your matrix A. And then when you think about the nodes that are inside the subdomain, they are somehow here, not necessarily together, but essentially this is a subblock. And then what you do is that you are inverting not the whole matrix, but you are inverting pieces, little pieces of this matrix. And that the sum of these inverses will be an approximation for the inverse of the whole matrix. Okay. And for this simple preconditioner, you can prove that the condition number of the preconditioned system is bounded by a constant that is independent of the geometric factors and depend on capital H, which are the size of the subdomains, and delta, that it's a measure of the overlap between subdomains, which is an improvement. I think I didn't mention it before, but if you compute the condition number of the original matrix, it's always of order capital little h squared to the minus 2. Little h is the size of the original elements. Okay, so that's essentially why you're required to precondition. So this one, this approach has one problem. It's again, it's quite simple, and if you think only in the algebra in the matrix, what you're doing is just taking sub-blocks and inverting each one separately. It has one problem, and the issue is that when you put more subdomains, the condition number blows up. Okay, and that's essentially because if you have n subdomains in this line, if you are solving independent problems, you don't have communication across all the subdomains. Okay? So this is why a second level is required in order to get an improvement in the condition number. So what you do is you now have, you define, let's put it here. So these are called the local problems. Now what you do is, okay, well, somehow you're going to select some degrees of freedoms all over the domain, and they will create what we call a global space of dimension as small as possible that will keep track of information all around the domain. So the second level preconditioner is the same as the first one, where you have these local corrections, but then you add a similar term that relates to the course problem that I will define in a couple of minutes. And if you do this, then the condition number improves. Now it's independent of the number of subdomains and only depends on capital H over delta, which is like the relative size of the overlaps of the decomposition. Okay. Okay. So just a brief summary. One level works fine. It's quite easy to define because you are only inverting subblocks, but has the scalability issue. And the two level, what you do is then you include a core solver, which makes it scalable. Okay. It goes in slow motion. Okay. So this was the first half of the talk. Essentially, what I wanted to convince you is, okay, well, if you discretize a PDE, you end up with a linear system. In this case, it's symmetric. You can use conjugate gradient. If it's not symmetric, it's not a problem. There are other families of solvers that are called GMRES, generalized minimal residuals. And in order to solve the linear system, you can construct this precondition. So there's a WhatsApp phone call. I don't know. Okay, well, the next part, I'm going to try to talk about two ideas. Okay. One is what happens because this business started maybe 50 years ago. And what they did is, well, your decomposition is going to be regular, meaning that these subdomains are triangles or squares. Okay. Like 15 years ago, the natural question was, well, what happens now if your subdomains are somehow irregular? Okay. And we developed some theory in what they call Jones domains, which essentially allow you to have like these irregular interfaces on the boundaries. This is basically work that I did in my PhD thesis 10 years ago, something like that. And then also I'm going to talk about what happens when you have high contrast, meaning if you remember in the PDE, we have this coefficient kappa. Then if the maximum of this coefficient over the minimum, which is called the contrast, is too high, then the bound will deteriorate because the condition number, which I call cont, the condition number of the matrix is similar to this contrast. Okay, so if you have high jumps in the coefficient, you also will have a slow convergence. Okay, so here I'm going to talk about these two ideas that we put together like 2 years ago or 1 year ago, I don't remember. That's work with Juan Galvis. Uh, I'm not sure if I can go next because, excuse me, because the window is not selected, so I think I cannot go. Okay, thank you. Okay. So as I was saying, the first idea is, well, what do you do when you have these irregular boundaries of the subdomains? Okay. Um, it is not natural to define functions there because, again, if you have triangles or squares, you can define linear by linear functions. And once you study virtual elements, it seems like a natural idea to put ideas together of virtual elements and these irregular polygons. This is on previous work, as I mentioned. This is almost 20 years ago by Dwildon and collaborators. Um, so, as I mentioned, you have your domain, you divide it into subdomains, and then create overlaps. And at one level, it's quite easy because you only have these zero extension operators, and then you invert locally. Okay? Always the problem is what you do in the core, which is this one here. How do you select these nodes, and how do you interpolate? Because at the end, what you do is like you have two meshes. You have, oh, I have the picture there. Uh, you have like two levels, meaning that you have the fine mesh, which is in this case these small triangles, and you have the coarse mesh, which is the one that it's colored here. So you somehow you need to move from the coarse mesh to the fine mesh and back. So the first idea that my advisor worked was a little bit, um, I don't want to say simple, but is the naive approach that you would try first. Um, and it worked, hopefully. And then what you do is, okay, you define these coarse red nodes, which are the nodes of the coarse mesh that belongs to at least three subdomains, and you will define one function per node. Okay? There, you have the same idea. I'm just going to show a picture here. Then what you do is you have a canonical function, meaning that you have the value 1 at one node, 0 at the other nodes. But then what you do is that you go as smooth as possible. Since we are solving Poisson equation, you know that your solution should have a small, the energy should be as small as possible. So what you do is you try to create a coarse function um, that has only one degree of freedom on the coarse mesh that changes as slow as possible on the fine mesh, and that's enough. This is like how all the functions would look like. Um, and again, just to give you an idea, the function takes the value 1 at the vertex that is in yellow, and then what you do is you move linearly in the directions of the other interfaces. My advisor did harmonic extensions, which are not necessary. You can do cheaper versions. So this is a most recent work, where essentially what you do is you define these values on the boundary, and then instead of moving to the interior with harmonic extensions, you compute polynomial approximations, which is again cheaper. And so there are several ways to do that. Here, from the theoretical point of view, you require several tools in order to do the analysis. I'm not going through the whole details here, but I'm just showing you what you need to get bounds for the condition number. You always require some type of Poincare inequality, discrete Sobolev inequalities, some interpolations because you need to move between the fine and the coarse mesh. You also need to project in the case of virtual elements. So these are sort of tools that you need for to develop that theory. Okay. At the end, you end up with this type of bounds. This one again is for the case of these irregular partitions. So when you have these irregularities, you have this extra term, 1 plus the logarithm of capital H over little h, which is in practice not a problem. Usually in numerical experiments, you don't see that term of the bound. Usually it remains constant, but theoretically it could appear. Okay, so this is like the first idea. Again, you can handle irregular subdomains by defining just a few functions that have this shape. The second idea is about high contrast coefficients. This is work by Juan Galvis and collaborators. Juan Galvis is from Universidad Nacional de Colombia. Again, the idea here is, well, what happens now when you have a high contrast? And as I mentioned, the condition number of the matrix grows linearly with the contrast. Okay, so that's also a problem when you solve these PDEs. When I say high contrast coefficients, you can think of this. There is this coefficient kappa that takes the value 1 in the background, and then you have these inclusions or these incisions, channels, and whatever. And then in these incisions, the coefficient takes a value eta, which is greater than kappa. And here, when we say multi-scale coefficient, it means that we have several of these channels all around the domain, and the contrast is high enough. Okay? I will show you some pictures later. So again, just to give you an idea of what the theory looks like in this area, always when you need to bound the condition number of the preconditioned system, what you need to do is to get your function B, your virtual functions, and split it into pieces. Each piece lives in a local and a global space. And what you need to do is to bound the energy of these little pieces in terms of the whole function. Okay? So that's always the main issue when you try to get bounds for the condition number. Okay. What happens here is, well, when you try to when you write down what you need to estimate, okay, then turns out that you end up with some sort of estimate, the first one that appears here. So you need somehow to bound the difference of the function and the coarse component in terms of the L2 norm. And then the natural way to do it is using generalizing value problems. Okay. So what you do here, I think it's later, but so if you have your subdomains here, what you're going to do is you pick one subdomain vertex, you take all the subdomains that are shared by this node. This is what we call omega I. And then you have to solve these local eigenvalue problems on these subdomains omega I. And what you do is essentially you expand your functions in terms of the eigenfunctions that you get from this eigenvalue problem. Okay, so once you solve the problem, sorry, now I understand. It's like, okay, so you solve the eigenvalue problem, you take the spectrum and you order it, and then you take the first L eigenvalues, and then you project your function into the space generated by these first L eigenvalues. And eventually there's an easy way to see it. I will show it to you in a graph in a couple of minutes. But then when you do that, then you have like a local interpolant, which has this form. Again, it's a projection onto the space of the first L eigenvalues. And then you can prove this type of estimates. The L2 norm of the difference of the function and the coarse component is bounded by the energy of the whole function, multiplied by the eigenvalue that you did not take into account. Okay. In particular, when you take L equal to 1, kappa equal to 1, you get the standard Poincaré's inequalities. So this is somehow a generalization of that. So just to give you, okay, no, sorry, before that. So at the end, the space that I called before a coarse space, here it's called multiscale space, is the span of all these functions. Okay, these functions are obtained by the eigenfunctions multiplied by a partition of unity, and then you interpolate into the coarse mesh, because remember that what you want is you want one function per vertex, but defined in the whole space. And here again, since we are including more functions, then what is happening is that you are essentially using the coarse space that I defined previously, but with more functions that arise for the eigenfunctions. Okay, so again, this is just to show you an idea of what's going on. So to the left, we have a subdomain vertex. This is the domain omega I that I described here. Is the union of all the neighbors of that node. The small lines, the small channels, is the variation of the coefficient. So in this case, kappa is 1 in the background, and kappa is 1 million in these little channels. And to the right, you can see the eigenvalues of these problems. Okay, so the circles are the case when kappa is constant equal to 1, so when there's no jumps in the coefficient. And when you have these jumps, these high jumps, then what you see is the black dots. So you get 4 eigenvalues close to 0. So essentially, that means that in your course space, you need to include 4 eigenfunctions, because those are the problems when you compute the condition number of the preconditioned system. And that's geometrically easy to understand, because since you have 4 channels in the region to the left, then you know that you will have 4 eigenvalues close to 0. There is a proof that so that's easy to choose how the value L for the number of eigenfunctions that you need to include. And again, I have no time for the details, but then you can prove with this selection that the condition number of the preconditioned system, for this case of high contrast, the bound is independent of the contrast, and then you get this factor. In this case, we got a square factor of capital H over delta, which is the relative width of the overlaps. In practice, you only see linear growth, but well, in theory, that's what we got. So maybe there could be some improvements. Okay, and just to show you some numerical experiments. This is again like the case of regular and irregular subdomains. We have these channels. So kappa is 1 in the white areas, and we change kappa from 1 to 1 million on the red elements. Okay. And this is like a typical table of results. We have 2 rows, squares and metis. Squares is the case of the picture to the left, and metis is a graph partitioner that is very used in this area. Metis corresponds to the irregular subdomains that we have to the right. Okay? So as you can see, in both cases, as we increase eta, the contrast, when you do what was done before by my advisor and by me 10 years ago, you observe that the condition number grows with the contrast. Okay. Iter is the number of iterations that you run in preconditioned conjugate gradient, and V0 is the number of points of the course space that relates the whole functions. And the adaptive version is the one that's where you solve the eigenvalue problems. So as you can see, let's pay attention to the second numbers. So the condition number essentially remains bounded, 23, 21, 6, 5. The number of iterations of preconditioned conjugate gradient again remains bounded. And the dimension of the space grows, because that's the effect you need to do. You need to include more eigenfunctions as the contrast goes higher. And then with that, you can get condition numbers of the order of 5 in the case of high contrast coefficients. This is how the eigenvalues look in general, and this explains why, if you take a look for the squares and the metis in the adaptive version, you have more eigenfunctions in the metis case. And that's because essentially when you have irregular subdomains, you have more neighbors. And then in the case where you have more neighbors, it seems that in average, you have to add 6 eigenvalues. When you have squares, well, you only have 4 neighbors, then you only need to add 4 eigenfunctions. And again, we can repeat these problems. Okay, sorry, this is like the functions look like. Maybe the okay. Somebody's calling, not me. Okay, and these are some experiments for more general triangulations. So we have here hexagonal, what we call Voronoi meshes, which are more irregular. And again, you can see, okay, these are the meshes I'm talking about. And then we have like the results. Again, you can observe if you do not solve the eigenvalue problems, the condition number will grow with the contrast. If you do the adaptive version, then you can observe here in the second part of this table that the condition number remains bounded, and as long as the dimension of the space grows. Okay? And again, the iter is the number of iterations, which is quite good. In this mesh, we have almost 10,000 elements. And for that number of elements would be essentially only 34 iterations that you apply to solve the problem. Okay, I think I have 5 more minutes. Okay, just 2 more minutes. Okay, so all these topics are in this paper that was published 2 years ago. Okay, just to conclude, and to give you an idea of future work, this is, again, I said, well, I'm going to show this for the easiest equation, elliptic equation. You can use this for parabolic problems, and we are trying to expand these results for other PDEs. So here I show you a semilinear parabolic problem. And well, this is joint work with Juan Galvis, Luis Contreras, and Iván Velázquez. They are from Universidad Militar in Bogotá, Colombia. So again, you multiply by a test function, you integrate, you end up with a continuous variational formulation. Here, since we have time derivatives, what we got here is a new bilinear form, which is the mass matrix, essentially. And in the right-hand side, you have this expression. Okay? From the numerical point of view, then again, what you do is, well, replace the spaces. Or maybe this is the end. Let's see. Okay, there you go. So what you do is you replace the spaces with this multi-scale coefficient. If you I'm sorry. Okay, here again we have this coefficient kappa inside the divergence of this product. So again, we're interested in the case where this kappa has high oscillations. So the space that you define here as V0, the coarse space, is essentially the same one that I defined before, okay, where you solve the eigenvalue problems. And then, okay, then you end up from a discrete point of view in a similar problem, but now you test with functions in this multi-scale space. Of course, you need to take care of the discretization of the time derivative. That's not really a problem, but I just want to show you some preliminary results when they show up. I think the battery is dying of this thing, because now it's not blinking anymore. Oh, there you go. Okay. So just to give you an idea, again, we have, yeah, but well, this is gonna take some time. This is like the distribution of kappa and some mesh. And this is how you obtain the numerical approximation for these problems. We have bounds for the error estimates and so on. So you can do essentially many things here. Here is just like a table, just to conclude, on the error of the approximations, measuring the L2 norm and the H1 norm for particular problems. So what I'm trying to say here is these ideas of domain decomposition can be used, are usually used for elliptic equations, but they can be extended for different PDEs. Okay, so thank you so much, and this is just two pictures of the campus of University of Costa Rica. Thank you.
Thank you. Very nice talk. Do you have any question? In this last part, or even in the first part, you can you use Weblet framework? Because Weblet, I know that gives you precondition it directly by construction. Okay. Okay. Nothing else? Okay, coffee time. Thank you very much, all the speakers again. Thank you. Gracias.
Hola, hola.
I mean, is that like how do you?
No, it's just press one at once. If it doesn't work, just wait 1 second and then. Vamos a ver. So it's supposed to be 25 minutes.
25.
So I'm gonna remind you.
Yeah, I also have the
You have-
stopwatch. I plan to do like around 20 minutes.
Perfect.
Yeah.
Okay, so good afternoon. We're about to start this session. Our first speaker is João Fontinha from Faculdade de Ciências da Universidade de Lisboa. I'm sorry, don't speak Portuguese. That was my best. He's going to talk about Laplace transforms and these other topics.
So thank you very much for this invitation to speak at this wonderful meeting and conference with many friends. And so I'm going to present to you the work I've been doing with my supervisor, Professor Jorge Buesco. And it's a topic that fascinated me very much. And this is about the consequence of what's going to be on our future work. So let's start with some. So we'll consider like a Laplace transform of a locally integrable function as a bilateral Laplace transform. And I want to consider it as like a L2 Fourier transform on each vertical line. And we will assume that it has a vertical strip of convergence where it is allomorphic. And as you know, we have the standard uniqueness theorem for Laplace transforms, which is if we have two Laplace transforms coinciding on a vertical strip, then the functions, the determining functions, will have to be the same almost everywhere. So really the question is what happens when the strips are disjoint? So our function is allomorphic on the whole strip, and it has two Laplace representations on these joint strips. And so what happens, right? So we have the case first, we can have a non-zero gap where actually the strip that separates the representations is like a real strip. And this, from a trivial consequence of abscisses of convergences of each individual unilateral Laplace transform, implies that the functions must be different. So here, uniqueness can no longer be valid. More interesting is when the strip that separates is really only like a separating line. So here, both things can happen. They can be the same, and in this case, there's really nothing separating them, and we have a Laplace representation of the whole strip, or we can actually have them to be different, like Professor Buescu introduced, our so-called ghost transitions. So, I mean, Professor Jorge Buescu summoned the ghosts, but now it's also important to deal with them and possibly know how to get rid of them. So our talk will be really how to construct examples of ghost transitions, not only with just this invisible line, but also with a non-zero gap, and about conditions to prevent the ghosts from happening. So we need something to relate the two representations, like they're on these joint strips. What do we do? So we use a little analytic continuation lemma. So suppose we have F holomorphic on the strip, and it is represented by a Laplace transform over some line C, okay? And we use this theorem by Harper, which is basically a Gaussian convolution type of analytic continuation, where by convoluting by that Gaussian, we get a type of summation for the Laplace transform where that function, ft, is entire. And as t goes to 0, like as the Gaussian, it approximates the original function uniformly on compact subsets of the strip. Okay? And well, if we go over to the imaginary axis, right, we get that function which satisfies the ET equation, right? Just differentiating under the sign. And so now we come to our strategy. Suppose we have the two functions, we take the difference between them, and we plug in that function u, and we see that again it satisfies the ET equation, but this time it is 0 for time equals 0, and that's easily seen by taking the limit, and the limit is locally uniform convergence, so it extends by continuity, and we have this 0 condition. And we call such functions null temperature functions. Okay, so it's a terminology we will use throughout. So the thing is, interesting thing is, whenever both functions are different, then we obtain a non-trivial null temperature function. That is like a function which satisfies the ET equation as 0 initial condition, but it's not the 0 function. This can happen because we are on the infinite rod. And this can be easily seen by proving that that term is L1, the Gaussian times the phi, and it's because of our L2, initial L2 assumptions and the basic older argument. And this actually provides us with examples of non-trivial null temperature functions which are uniformly bounded with respect to the space variable. These are rare. Usually the original Tikhonov function does not satisfy that, depends heavily on the space variable. So really we have a challenge, which is to construct an holomorphic function on a vertical strip and with two distinct Laplace representations. So how do we go about constructing these examples? Okay. And so there are a few things that I want you to keep in mind and remind yourself. So we have this Pauli-Wiener theorem. It's not the original Pauli-Wiener theorem because that's for like only half planes, but Harper proved it for proved the generalization and actually a weighted generalization for vertical strips. And so if we have the vertical L2 norm inside the vertical strip, if it is finite, then we can safely say that f can be represented by a Laplace transform. And also, we must keep in mind that whenever we have a Laplace transform, that we have that vertical growth of little o of the modulus of the imaginary part. And this is important because if the function is holomorphic on that O strip, and if it has that O of y growth inside its domain of representation, then if we want to have then we need to break representation on that red strip, we need a very fast growth to escape the fragment Lindelof, which would force also that growth to be the same. So here is our strategy. Okay, you cannot really see the light blue, but let's consider the whole plane. And we want to construct an entire function. So this is now entire function theory, which is O of 1s on every vertical line, y, to use Pauli-Wiener theorems to extract representation. But on that red strip, we want to have very, very fast growth so that it prevents representation. So it's like, think about like bounded entire functions on every vertical line except on a strip or even only in one line. So that's going to be our strategy. So how do we do this? So we employ this technique of construction by Cauchy integrals, which I believe the first instance was used by Mittag Leffler back in the 19th century, I think. And we consider a function key, which is non-decreasing, and we consider that contour where we take just 1 over key and close it below. And we get that generalized Cauchy integral. And as you see, it has that age function there, which what is that function age? Will be the unique conformal mapping, mapping that horn region to the semi-half strip like that, okay? And then it's important that conformal mapping is very important because then by Halford's distortion theorem, we get the sufficient conditions for it to define a holomorphic function. So on the imaginary axis, the Halford's theorem grants us super exponential growth to violate Fragment-Lindelof. And on the curve, on the contour, we have super exponential decay, which makes the integral absolutely convergent, and it defines holomorphic function outside the region. So we have defined it holomorphic function. So we have so this is okay for S outside the region. And if we want S inside the region, I mean, we can just pull M up, okay, and change the M. But if we want to keep the M, we can just keep the M and add the integrand e to the h. Okay, so it's the same thing. So we want to keep the M. So we have that branch function. So outside it's just the integral. Inside you have to add that super exponential. It's like we are concealing a super exponential growth only to that region inside the horn. And well, and this function has the desired properties. So on every vertical line, it is bounded. It is actually O over 1S. It's actually a bit more difficult to prove. It's not that trivial to prove. And inside, due to Alford's distortion theorem, it grows faster than Fragment-Lindelof. So it's really a good candidate for us. So now, how do we extract the Laplace representation? We use that formula. We express the Cauchy kernel as a Laplace representation. And to the right of the contour, we connect by switching, by using that representation and switching integrals, we have that Laplace representation. And by increasing M, it steadily extends up to the imaginary axis. And we can keep M the same because actually that via Cauchy's theorem that the integrand over there is holomorphic, so it's invariant on M. So that's our function on the right, F1. Similarly, to the left, I mean, we get what we expect, like the same, but for a left-sided Laplace transform with a minus. And if we take the difference, we get that Hankel type contour integral. And plugging into U, we obtain this non-trivial null temperature function. So this is, if these functions are known to be, so we know that they are non-trivial because, I mean, we managed to do a phi with a non-trivial two Laplace representations. And if we didn't use that connection with the Laplace, it would be very difficult to prove that this is actually, it's easy to prove that it satisfies the equation, and it's zero on initial time, but it's difficult to prove that this integral is non-trivial because that age makes the whole thing very complicated in terms of Hankel integrals. But because we related to that connection with the Laplace transform, we can safely say that this is a non-trivial null temperature function. So concrete examples. If we take key to be linear, like 2I over pi. The 2 over pi is just a normalization factor. Then the contour will actually be an hyperbola, and we obtain, and we can use h to be that function, and we obtain already a very well-known, actually probably the first uh, known, known example of a non-trivial null temperature function, which was derived by Chong in his paper. If, on the other hand, if we take, okay, key just to be a constant function, then instead of having like a horn region, we simply get like a half strip, okay? And we get like, instead of a classical ghost transition, we get a strip where there's no representation. And the function, the h function, will be just like obviously a rotation. And we obtain Ferretti's solution. Like, so the only two known solutions in literature are special cases of this, of the conformal mapping H. So we get to now to the open problems, like what we are trying to solve now. So far, like, we were interested in constructing these ghost transitions. Of course, these are not, the Cauchy integral method is just one that we know, but there should be many more. It's just, this is coalescing into a problem on entire function theory. We basically, we want entire functions which have nice growth properties on vertical lines, but then on the imaginary axis they blow up. So this is then about entire function theory, and the Cauchy integral method was just one. But as we said, so how do we get rid of ghosts, right? How can we guarantee uniqueness when there's a zero gap, right? How can we say that F1, which conditions must we impose on F to ensure that the representations are equal? So there's this theorem by Harper, where if we impose some gross restrictions on the vertical L2 norm on F, like especially like at most exponential growth, then F1 is equal to F2 almost everywhere. The proof uses the uniqueness bounds for the ET equation. It's a very interesting proof. And my question is that bound sharp? So what do I mean by sharp? Is that growth, like that polynomial explosion around zero, like the best we can do, or can we like actually allow it to grow a little bit more and still prevent ghost transitions? So what do I mean concretely? I take a function, okay, I'll suppose it is continuous, like for simplicity, which explodes to infinity faster than polynomial. Like when I say polynomial, I actually mean inverse polynomial, okay? So like it explodes to infinity on zero faster than any power of 1 over x. And my question is, can I construct a ghost transition which, I mean, whose vertical L2 norm satisfies that bound, because that would prove the sharpness of Harper's bound. And this is a problem, okay, like the natural thing to do is to try with this Cauchy integral method and compute the L2 norm. But what is the problem? If I do that, I get an L2 norm, like I get something, if you use Cauchy integral methods, you get something of this sort: e to the x 1 over x or x. Okay, so I mean, this is still too big. Okay, it's bigger than polynomial, but it's not totally sharp, because you always you're always dividing by x, so you cannot get rid of this x. I think this is like a really not a bug, but a feature of the Cauchy integral methods. So the problem now is to tweak this to have more control over the L2 norms, and this is tied to okay. So it stopped working right at the end, but no problem. Well, no, but it's okay. So really, like it's tied to this following maximum principle problem. If we have, suppose that we have a bound on the vertical L2 norms of the function, and what is the maximal growth that I can allow for phi to ensure that it actually stays, the L2 norm stays finite. So really, it is, I'm gonna draw this problem like a little bit more. So suppose you have no information here on this line, but you have information on these lines. And here, these lines, the L2 norm grows like O phi of x, right? And phi of x blows up at 0. How big can this be so that I can ensure that the norm, the L2 norm here is also finite? And that's like probably the next formulation of the problem, and it's open. It's what we are working on, and I suspect we need to use some, I don't know, the Ormander L2 approximations using subharmonic functions. But that's maybe for a future talk. I think I want to stop here at 20 minutes and leave some time for questions. I hope you... something on the references. So the third reference, it's my paper and Professor Buescu and a colleague of ours, where we first constructed these ghost transitions. But this talk is about like further developments, which will come on a further paper. The Harper paper, which made the initial connection with the ET equation, is the fourth one. And the first two are actually like, they have nothing to do with Laplace transforms. They just focus on non-uniqueness of the ET equation. And this Cauchy which I erased, Cauchy method construction, I didn't initially find it through Kaneko, but posteriorly I came across Kaneko, that last paper, which uses this construction to study Fourier hyperfunctions with support at infinity. And that's it. Thank you. Thank you.
Thank you so much, Joao. Questions from the audience for Joao? Go ahead.
This is not a question, it's just a remark. The third reference, Fontina's paper, has actually been published in Integral Equations and Special Functions.
Perfect. Any other comment, question? Okay, so let's thank Joao again. So 25 minutes, 22. I'll let you know when 2 minutes are left. For the presentation. So we're about to start our second talk of this session by Mita Ramabulana. I hope I said it right. Thank you.
Just wait for the slides to load, actually. But this, of course, is a continuation or an extension of Elena's talk that she gave earlier this morning. So if you were there for that, then you should be more or less prepared. And of course, I'll skip some of these details, and just show a different extension. So, okay, of course, the topic is duality for these Delsat type extremal problems, and the setting is on compact Gelfand pairs. And this is joint work with obviously Elena Bedasheva, Balint Farkas, Marcel Gal, and Szilard Reves. So I will start with the motivation, and the setting is a Turan problem on the d-dimensional sphere. So of course, this is a familiar definition of our sphere. And our first definition is what we'll need is a kernel, which we also saw yesterday from Professor Buesco's talk. So we say that a kernel phi is positive definite if it satisfies the following inequality, which should hold for all choices of points on the sphere, as well as all choices of complex numbers for any natural number that you can pick. We also need the notion of an isotropic kernel. In this case, we will start with considering the spherical distance between 2 points. So theta of xy is just the grid circle distance between 2 points on the sphere. And we'll define a kernel to be isotropic if its values on the 2 points doesn't depend on their locations, but rather on the distance between the 2 points on the sphere. In other words, in this case, a kernel is isotropic if it can be factorized as follows, where big phi is equal to some small phi composed with theta of xy. And just for some notation, we'll denote this class phi CD to be the collection of all continuous functions phi on the interval from 0 to pi, with a normalization that phi of 0 is equal to 1, and such that the associated isotropic function is positive definite. And we also have a decay condition that phi of t is equal to 0 as long as t is greater than or equal to c. And now we can state the Turan problem, which should be familiar from Elena's talk. In this case, we are interested in finding the supremum of all integrals of kernels that range in our class. And in this case, we are going to integrate with respect to the surface measure, and x is an arbitrary point that we pick. And it's easy to see that this integral doesn't actually depend on the point x that one picks. All right, so this Turan problem for the sphere is an open problem that was posed by Professor Tilman Knighton in a paper in Bernoulli that appeared in Bernoulli in 2013. And I think his interests were some kind of applications in spatial statistics and climatological modeling and the such. And in his setup, the positive definite kernels appear as correlation functions, and the sphere models the surface of the planet Earth. And the data, of course, as I mentioned, is this kind of statistical modeling. And one can interpret physically what these kernels represent. In this case, if phi comes as the covariance of a real random field, then this quantity, this integral, simply represents the total influence of Zx with the rest of the field. And so one can interpret the supremum as basically the maximal total covariance that can be concentrated locally around the point x without violating the condition of positive definiteness, and while ensuring zero correlation away from the point. In this case, one can imagine that if you're studying influence of weather, as you move away from the point, then the influence of the weather conditions at that point decays as you move away from that point. So this is rather where this decay condition comes from. All right. Right, now I'll talk about a generalization of this. So there are 2 points of departure in this generalization. The first is that we can obtain the sphere as a quotient of SOD plus 1, quotient with SOD. And in this case, we see that the sphere is a homogeneous space. Secondly, Uh, Now that we've left the setting of the sphere and we are replacing it with some more general homogeneous space, we lose the metric, which means that we need a replacement for defining what an isotropic kernel should be. In this case, it's easy to see that a kernel is isotropic if it's invariant under the action of our group SOD plus 1, right? So in this case, with these two observations, our setting is a locally compact group, G, with a compact subgroup that we call K. And then in this case, G over K is, and just for some notation, we'll denote by GK the coset of K containing the point G. Maybe I should point it. Doesn't seem to be working anymore. Great, it's working now. Point that way, okay, great. In this case, we have the Weyl integration formula that connects integration on our group and integration on our homogeneous space. So this is some kind of Fubini type theorem. Doesn't matter where I pointed, the heaven or that, it doesn't matter. Okay. Yes, I think so. Kernel, in this case, is positive definite if it satisfies this familiar inequalities. Should be reminiscent of what we saw in the sphere. And a kernel is G invariant if it satisfies this invariant condition with respect to the subgroup K. In this case, the two-run problem, I should have maybe explained this, that one can imagine that we have our sphere, and then we have some spherical cap of radius C. And in this case, when we have a homogeneous space, we want a replacement for what this should be. And in this case, we'll define a subset U to be K by invariant if it is symmetric with respect to left-right multiplication by the group K. So you can imagine the group K in this case to be, so we have SO3, and we have SO2. And in this case, if we take a spherical cap and we rotate it left and right, then it remains fixed. So this is our K by invariant condition. It's some kind of radial condition, of course, if you want to look at it that way. So in this case, we take U to be a K by invariant compact neighborhood of the identity. And we denote by this F sub G over K of U to be the collection of continuous positive definite G invariant kernels that satisfy, firstly, our normalization condition, secondly, our decay condition. And in this case, the two-run problem asks for the supremum of integrals of that form. And of course, in our specific situation, we get back to the sphere. Originally for my PhD, I was mainly looking at the two-run problem and the delta type problem for locally compact abelian groups. And in that case, there are some techniques that depend on the structure of the groups to obtain estimates and all kinds of questions, such as the existence of an extremal function. But when we're looking at the case of the sphere, it wasn't clear that these methods can be applied, and we struggled a bit to find to answer some questions, such as the existence of an extremal function, until the observation that since we have our homogeneous space, which is being acted on by the group, it might be possible to connect the two-run problem on the group, on the homogeneous space, to the two-run problem on the group, and maybe leverage some of the techniques on the group to be able to say something. So in this case, we'll exploit a particular bijective correspondence. And in this case, we will first require the following definition of a positive definite function, not on the homogeneous space, but on the group, which you've seen at least 2 times in this conference. So I will just skip through it. And I'll also define a function to be K by invariant if it's symmetric under left-right multiplication by the group K. And we have a sufficient supply of this K by invariant functions, because for any compactly supported continuous function, we can simply average on the left and average on the right to obtain a K by invariant function of this kind. So we are in a class which has enough functions, I suppose. And the sort of key theorem that makes this connection is this following, which we sort of discovered naturally when we were trying to connect these problems, but it appears sadly, maybe not sadly, that it's folklore and no one bothers to give a proof because apparently it's just so simple, right? And in this case, the idea is that if we start with a K bar we start with a G invariant kernel, big phi, then we can define a K bar invariant function on the group using this formula. And then we can go back, of course, by starting with a K bar invariant function on the group. And then using this formula, we define a G invariant kernel. And this sets up a bijective correspondence between the class of continuous positive definite G invariant kernels and the class of continuous positive definite K bar invariant functions. And so we have the following theorem that under our setup, of course, G is a locally compact group, K is a compact subgroup. We have our bijective correspondence. And in this setting, we have that the normalization condition that we have on the kernel translates to a normalization condition on our group. The support condition or decay condition on the kernel translates exactly to the support condition on a function. And lastly, through the Weil integration formula and the fact that we normalize the Haar measure of the group K to be 1, we have the following equality of the integrals. And now we can state the Turan problem on the group. So far we saw the Turan problem on the homogeneous space, and we established some connections with functions in the group so that now we can state the Turan problem on groups. And this is, of course, we have a function class fkg of u, consisting of normalized functions that are supported in u, are continuous and k bar invariant. And the Turan problem in this case asks for this integral. And the considerations that we saw above tell us that the Turan constant from the homogeneous space is exactly equal to the Turan constant that we obtained from the group. So these problems are exactly equivalent. And so instead of looking at the problem on the homogeneous space, we can run away and go to groups and say whatever we can and translate back and forth depending on what we want to say. And one interesting application of this is a proof of the existence of the extremal function for the problem on the homogeneous space, because it turns out that you can use quite a lot of harmonic analysis on the group to answer the question of existence of extremal function and then translate back. Right, now we consider a generalization of this problem. Well, we take two sets in this case, a set of positivity and a set of negativity. And we have some natural symmetry and topological conditions on the sets that I won't bother about. And then we consider the following function class. It consists of k bar invariant functions with natural normalization conditions and sign restriction conditions. And we consider the sort of following Delsat type problem. In this case, the problem, as you've seen, is interesting in locally compact abelian groups. And for the non-commutative setting, this was introduced in my PhD thesis. And the motivation was, of course, the Turan problem on the sphere. And of course, I won't say much in this case. Elena already spoke about this, but if we consider different sets for the sets of positivity and negativity, we obtain the Turan and the Delsat problems. In this case, it may seem like a generalization for its own sake, but it turns out that roughly around the same time that we generalized the Turan problem to homogeneous spaces, a result appeared due to Maximilian Wackenuth, who was answering a conjecture by Korn and Zhao about finding upper bounds for packing density on hyperbolic space. So you saw how the Delsat problem gives upper bounds for packing densities in RD. One can do the same construction on certain classes of Lie groups and show that the Delsat scheme gives you an upper bound for packing density in hyperbolic space. So in fact, our generalization of the Delsat problem actually extends to those cases as well, not just on the sphere. So in this case, we are going to do linear programming, and we're going to try to find a strong duality relation for the non-commutative case. We'll restrict ourselves to the compact case for compact Gelfand pairs. This is one defect of this theory, that it doesn't extend to non-compact groups. and it's specifically designed for compact Gelfand pairs. So we say a pair GK is a Gelfand pair if the L1 algebra of K by invariant functions forms a commutative algebra under convolution, right? So in this case, we have a group that is not commutative, so we lose characters, and we lose much of the harmonic analysis on that we have on locally compact abelian groups. But we can look at the L1 algebra, and if that L1 algebra turns out to be commutative, then we can define characters and use roughly this sort of Gelfand transform to obtain some harmonic analysis on the class of K by invariant functions. So we do have some commutativity. We don't lose it. We lift it from the group to the function space. And our replacement for characters is that we define a spherical function for the Gelfand pair to be a continuous function that satisfies this relation. And one can appreciate what this really means. In the case where K is the trivial subgroup, this just turns out to be the multiplication formula that is satisfied by exponentials or characters. So this is basically an averaging of that kind of formula. So it's like a character identity. Right, and a spherical function one can show is necessarily K by invariant. And we will denote by gamma the collection of four spherical functions, and we'll call it the spherical dual. Oh, come on. Yes, I learned from you, yeah, so. Right, and we have the Peter-Weyl theorem, which gives us an orthonormal basis for L2 functions on a group, can be specialized to the case of K by invariant functions, and it will give us that any K by invariant continuous function, which is positive definite, has this expansion with non-negative coefficients. And so for the linear programming duality, again, we have two pairs of spaces. Our first space is L infinity, and its dual, we take L1, and we fix a positive cone. In this case, like again, like in Elena's talk, we take the collection of non-negative functions, and its polar in the space is just, again, the convex cone P star, which I denote like that. And for the second pair of spaces, we take F to be the collection of continuous K by invariant functions. And in this case, for the second pair of, for the dual, we'll take the collection of K by invariant measures, right? We could take measures, but it would turn out that if you take a measure and you take its periodization, then the two give you the same value on any K by invariant functions. So this will violate the condition of a bilinear form being separating. So we need to restrict our measures to simply K by invariant measures. Again, we have a periodization of K by invariant of measures. So if we take a measure, we can simply average it on the left and the right to obtain a K by invariant measure, the same way that we do with functions. So now we can also sort of explain the positive cone that we take for the collection of functions. So let me go back. We take our convex cone Q to be the class of functions that satisfy the sign restrictions. And then we consider the following function class. This is simply what we had before. And then the extremal constant for our class can be sort of explained as follows. Instead of this problem, we will simply translate it by taking Fourier transforms. And just like before, this gives us the following problem, where we have U. And the two problems are connected as follows. And then again, we need an adjoint operator to connect with the second pair of spaces. And then again, we can write our extremal problem as follows using the operator T. And again, we obtain our adjoint operator, which allows us to describe the dual problem. So this is our primal problem U, and the dual problem can simply be described as follows. In this case, I should remark that the Aristov-Bambenko scheme does not work for two-sided conditions. So it was a non-trivial step for us to extend it to work for two-sided conditions. So it works for the Delsart, but it doesn't work for the two-run, but in our case, it works for the two-run problem. And this is both true not only for locally compact abelian groups, but for compact Gelfand pairs. And just to say more, either way, the two techniques don't work for non-compact, locally compact groups. So a different argument is needed there. And in our other paper, we show a duality theorem for locally compact abelian groups, which leaves open the case of when our group is non-compact and non-abelian. We believe that we have some techniques to handle that case, but it needs a bit more work. I will just state the main result in this case. We put a natural topological condition on our sets. And then we of course are going to generalize a few things in our problem. We're going to generalize the normalization condition. And in this case, we take a different linear functional sigma, which we are required to satisfy Wiener's condition, which is simply that the Fourier transform is strictly positive. And in this case, we consider the more general problem. A special case of this, depending on what linear functional you put in the normalization, will give you the Delsart problem. And of course, the functional in number 6 is not linear. So by some normalization trick, we find a linear version of that problem. And to describe the dual problem, again, we take a collection of a different collection, T0 of GK. And the dual problem in this case turns out to admit the following description, which should be familiar from the earlier talk. And our most, well, this is one of the theorems. This is, actually, this is our most general theorem, I should say. So for a compact Gelfand pair and omega plus, omega minus being K by invariant symmetric Borel sets, with omega plus containing the identity and satisfying assumption O. Another assumption that we'll need. Oh, come on. Don't fail me now. Great. If we assume that the measure takes the following form, where T is positive definite K by invariant and absolutely continuous with respect to the high measure, then we have the following strong duality relation. Of course, special cases of this will give you the Turan and the Delsart problem, but it might be interesting to consider more general linear functionals. This was what we were trying to do, but we couldn't generalize it as far as we wanted to because we couldn't replace the integral by some more general linear functionals. So this is where the Aristov-Babenko scheme also fails. And this is why our other paper, which works for locally compact abelian groups, actually is better because it does this for arbitrary linear functionals, not just the integral. Anyway, that's the end of my talk. And I should thank you so much for listening.
Thank you so much, Mita. Questions, comments?
Thanks for your talk, Mita. It was very interesting. In fact, the beginning of our talk took me back about some 20 years or so because the engineering, the problem which sparked my interest in positive definite functions was exactly one of those covariant matrices in which the engineering people were interested in Fourier transforms. So thank you for that. I would like to ask you if you have looked into the machinery of reproducing kernel Hilbert spaces related to positive definite functions or not.
I have not looked at this, no. I mean, I've seen reproducing, but I haven't looked at the machinery at all. Okay, thank you. Yeah.
So no more questions. We thank Mita again, please. minutos, ¿verdad? Cualquier cosa, si te veo ahí que vas con un poquito de tiempo, te aviso. Okay, so we're about to start our third talk of this session by Guillermo Gordillo Núñez from University of Coimbra. So, Guillermo, thank you.
So, hello, thank you all for being here. So it's going to be a radical change of topics. I'm going to be speaking about orthogonal polynomials in general. So I don't know the love towards orthogonal polynomials in the room. I know some people that they really love it here, but I don't know if maybe it's your time to go away if you don't like it. No? Okay. So, well, since I know some people, they don't work in the area, I'll stick to the very basic, and it's all going to be very elementary in the end. So in general, in the field of orthogonal polynomials, what we study are orthogonal polynomials, right? And we have different families. And what people like to do to publish is to define families and families and families of orthogonal polynomials. They usually give them some names, and they are usually advertised as new in some sense, maybe in an algebraic sense or in a classical way. I will clarify later on what I mean by classical. And here in this talk and in the next one, which is going to be given by Kenya, we want to address like a class of orthogonal polynomials that has been appearing lately in the literature that are sold, that are advertised as new, but in reality they can be explained by means of the standard classical theory. So I'm going to be talking about what are usually referred as parafamilies. In particular, I'm going to talk about this para-Crabtree, para-Raka, and Q-para-Raka. And in the next one, Kenya will talk about what is usually referred to as -1 families. So the main idea that we want to transmit with this talk and the next one is that, the orthogonality representation is not something intrinsic of the properties of the orthogonal polynomials, and to define classicality is more related to the three-term recurrence relation and another characteristic that I will explain later on. So in the case of the para-Crabtree, para-Raka, and Q-para-Raka polynomials, which are the one that we are going to talk about right now, they're usually described as orthogonal on a bilattice. No, I will talk about these three families a little bit more in detail. So they have different origins, and usually it's related to physics, right? So in particular, this para-Crabtree family was introduced when trying to solve what they call finite XX spin chain, whatever that means, right? While trying to find what is called a perfect state transfer, which is used theoretically like in quantum computation. But okay, like I'm not going to go into any of those details. And they're usually described as being orthogonal on a linear bilattice. And it's said to be like a new kind of algebraic and orthogonal property of these families, of the family. Also, the para-Raka polynomial were introduced as a truncation/limit procedure of the Wilson polynomials. And this Q-para-Raka polynomial were kind of a Q generalization, whatever that means, right, of the para-Raka polynomials. And the three of them are described to be like orthogonal, in a bilattice, and this bilattice has a different flavor depending on the family. So in the case of the Paracracio, they are like a linear bilattice. In the case of the Pararaca, they're called quadratic bilattice, and in the case of the Q Pararaca, it's Q quadratic, right? Makes sense. So that's right, and this description of this orthogonality, like I wrote there, is promoted to a new kind of classicality. But I will try to explain that this is not valid if we understand classicality in the more traditional way. Okay, so to keep things simple, I decided to include the definition of orthogonality. Of course, orthogonal polynomials are polynomials. I got a sequence. For each degree, I got a polynomial, and they are orthogonal, of course. In particular, this orthogonality, well, in the more general way, it's with respect to a functional that lives in the dual space. And here I got the functional acting on the Pn times Pm, and the delta gives the orthogonality, right? Of course. And this, depending on the type of polynomial that we are working with, this functional may be represented in different ways, no? For instance, it could be an integral, right? And that's the usual orthogonality that is related to the more classical families, which are the Jacobi, Hermite, Laguerre, Bessel, and so on, which are the family that everyone knows and are usually called continuous classical, or something similar along those lines. And also it could be like a finite sum, which is well, weighted by some omega s, right? And some points in the space. And usually the orthogonal polynomials that are orthogonal with respect to a functional that can be represented that way are called discrete classical. No, and there we would find the usual Hahn, Meixner, and so on families. So in the case of the Pararaca and Gupararaca, instead of having one finite sum, we're going to have two finite sums, and that's why they're called orthogonal on a bilattice. So to make things more explicit, I wrote it there, no? We're going to denote the Paracracio Pn, and can I go back? Like, okay. So this xs there now is substituted by a ys, and the thing is, they call it a bilattice because this term here, -1 to the s, alternates and gives like two linear lattices that are these two here, right? Which are not exactly the same, and of course give like two series of points on the space. So I'll draw it. It's quite straightforward, right? So it's simply the even numbers comes from the 2r, of course, which is when the -1s is even, no? And let me square them, why not? And so on. And then we have, well, this gamma parameter is kind of displacement. So, well, this is one, and this is gamma. And this gives the other points on the lattice, no? It's gamma, then 2 plus gamma, no? Yeah, and so on. And this gives like two linear lattices that are like intertwined by that term -1 to the s, no? And we, well, I'll show it here. And using those two strings of point, one can define like two different, so each string has like different omegas, and one defines different functionals in terms of different omegas, you know? So here I would denote omega square s. Oops. Delta, so on, no? 2s would be And then the orthogonality would be like a sum of the two lattices, no? Okay, simply that. Because it is written in that way, they call it classical in AB lattice. But the thing is that this representation is very easy to be deformed, to be transformed in other kind of representation. Instead of writing it in terms of AB lattice, okay, I'll go back. Instead of this ys, I can like deform the indices s here and express the same orthogonality instead with respect to, let's say, bilattice with respect to a linear lattice, a lattice that with this C, which is arbitrary. So I have like an infinite way of representing this orthogonality. So if I'm going to define classicality through the fact that they are orthogonal with respect to a bilattice, this notion is not like preserved by this simple fact. So as a way of describing this polynomial is a little bit out of the ordinary. It makes no sense. Like it cannot be advertised as something new. Also, usually when one speaks about classicality, this is related not to the representation of the orthogonality, but rather to the fact that the family satisfy a differential equation. So that's the hypergeometric differential equation that was studied by Bochner, where phi and psi are like polynomials of degree at most 2 and 1, and they're usually written the way that I wrote down there. And of course, when we say classical, it's more like historically classical, which are the first orthogonal polynomials that were defined that are related, of course, to application to physics, and in particular, these, like, there are many systems in physics that could be reduced to that kind of shape. So that's why they were introduced in the first place. So classicality, again, is not related to the shape of the orthogonality, but rather to the fact that they satisfy a differential equation. And if we try to use the above machinery and the above bilattice to form like a differential operator, it doesn't work nice with the orthogonal polynomial. So that's another reason to not pay attention to this kind of nomenclature when speaking about this kind of family. Also, well, a side note is that this Bochner equation is equivalent to the so-called Pearson equation, which is like a differential equation that the functional satisfy in terms of instead of the other orthogonal polynomial. So I won't go into detail, but simply every time you see like the Pearson equation with the phi and psi and the u is completely equivalent to the Bochner equation. So that's what I wanted to say. And the thing is that, well, depending on this can go like a little bit more complicated, depending on the geometry of the problem. The usual derivative can be substituted by a approximation of the derivative, which is formed by different lattices. Now that's a little bit what I was talking about before. So for them, that B lattice was something that could be used to define like a derivative, but if one takes a look inside of the structure that it would give if one tries to form the derivative using that B lattice, it doesn't work. Actually, so that this makes sense and one can define like an analogous Bochner equation with this kind of derivative, there is only like a number of valid lattices that are usually attributed to, well, this definition is usually attributed to Nikiforov, which are these three cases, and another case that Kenny will talk about in the following talk, which is simply the quadratic, right? The linear is a particularization of the quadratic one, and the q-quadratic, which actually converges to the quadratic if one makes q 10 to 1. So here we have three different families of lattices, but each lattices has like many parameters, right? So there are like an infinite type of lattices, and if a family is classical with respect a lattice, we need to determine with respect to which lattice, that means to determine also the C4, the C5, the C6, or the Q and the rest of the parameters, right? Right, and the thing that I want to convey in the next slide is that these parafamilies that I introduced before that were described as classical with respect to this B lattice, this, well, I didn't write it, but this Y of S, which made this alternation here, they don't need to be cataloged as new classical, and they can be fit into this kind of a structure, and they can be seen to be classical with respect to the usual standard machinery of classicality in the field of orthogonal polynomials. So the way that I want to do it, yeah, is to reconstruct the Pearson data, or like the phi and the psi and the lattice, using the three-term recurrence coefficient that appear in this equation. So this is a very elementary result in orthogonal polynomials, simply that if a family is orthogonal, then they satisfy a three-term recurrence relation that can be written in that way in terms of this parameter Bn and Cn. So knowing the orthogonal polynomials themselves is completely equivalent to knowing the Bn and the Cn. So what I want to do right now is to construct like an algorithm, like a method, so that if one feeds the algorithm the Bn and the Cn, one can determine whether this family could be classical with respect to the standard way without needing to resort to new definition of classicalities, and reconstruct like the lattice with respect to which is classical, and the phi and the psi. And that can be done very straightforwardly because, well, there is a lot of work that has been done already. And the thing is that we know the shape of the Bn and the Cn if we assume that the family is classical. So of course, here there are a lot of data, no? So don't lose yourself. Simply we have like Bn and the Cn are like the data we want to use, and we know the dependence of the Bn of the Cn in terms of the parameters of the classicality, which are these A, B, C, and E, which are like the coefficient of the phi and the psi, and this beta and this kappa, which are related to the parameters of the lattice and have the definition. So the idea is that I have an infinite number of beta n, of Bn and Cn, and I want to determine like 6 parameter. So it's actually very simple to simply brute forces, no? Use brute force, try to form a system choosing adequate Bn and Cn, and try from that to solve the system and to obtain the at least some candidate for the classicality. That is done very straightforwardly, and actually one obtains like these parameters that I was talking about before that define classicality in terms of this on the first coefficient of the three-term recurrence relation. Of course, we are not going to be using the higher ones. And also in terms of A, and then A, which was the coefficient, the coefficient for the phi, can be solves this cubic that can be reduced to a quadratic in the most simple case. So this gives us like some candidates for classicality. Actually, you can see like the actual data is explicit in terms of the Bn or the Cn, no? Of course, this is like a necessary condition, but afterwards one can use like the theoretical formula and compare. We know more or less like the dependence of n of these coefficients, so it's easy to compare term by term if we expand it in terms of the n. So this idea, which is very straightforward, no? Which is simply to brute force it and to solve a system and to try obtaining the parameter by simply operating actually works. And this way we can construct like an algorithm, like a series of results that are used to determine whether a family could be classical once the Bn and Cn are given. So well, there are like a series of steps that I won't go into detail, but I will simply show how it works for these families that I introduced before. And this way we will see that they are classical in the standard way, and we don't need to resort to new definitions. So firstly, I will talk about the Pararraca family. So the orthogonality was written in a similar way. I won't draw it because actually, well, I mean, I don't think it's necessary. And of course, these family were introduced in terms of the three terms recurrence relation coefficients. So we have them here. So it's this Bn and this Cn that are written in terms of this calligraphic A and calligraphic C. But okay, like we got the data and we can put all these coefficients into the formula before. And we obtain, in this case, a quadratic for the A, right? The leader coefficient of the phi, and we obtain like two candidates. If we solve it, right? Then we would need to feed this A into the formula before. I will go back just to show it once, no? And that formula, this gives all the data. I know. Ay, perdón. Okay, that gives all the data, and we can construct all the classicality data and then compare if they could actually be classical. So in particular, like I said, we have like two candidates, but if they are classical, it's only with respect to one lattice. A equals 0, the set of data that gives fails the test, and the other one succeeds. And it gives us that the Pararraca polynomial are indeed classical with respect to a lattice minus s squared, and this is the phi and the psi, the Pearson pair related to the classicality. Perdón. Okay, one can do the same procedure for the Paracrapchuk polynomial, and it works exactly the same. So I won't go into much detail, but surprisingly, I mean, well, not surprisingly, since I've been telling you, actually, we also obtain that this family is classical in the standard way, no, with respect to the lattice 2s, and the Pearson pair is the phi and psi given there. And one can do exactly the same procedure instead for the quadratic lattice to the Q quadratic lattice and reconstruct and obtain the same result. So I won't go into detail, but this method works for the Kupararaka polynomial, and in this case, we reobtain this, that's called Q quadratic, right? And this is the phi and the psi associated to the, well, I didn't write all the parameters because they were like too long. This is a little bit of a summary, no? So that's something that I wanted to convey, no? That these people introduce a new concept of classicality that didn't need to be introduced, and we have been able to recover the classical data by simply using the most elementary data of orthogonal polynomial sequence, which is its three-term recurrence coefficients, and we have been able to construct the lattice and the Pearson pair. And finally, we can use this well, the fact that we have described all of these families using the standard theory to actually understand what is the meaning of this bilattice. Notice that I'm using the thing is not to denote that I don't actually believe that it denotes some property that is worth mentioning of the family. But well, the thing is that instead of usually when one solves the like a classical family, one starts from the Bochner equation. But if instead of working with the Bochner equation in the direct space with the polynomials, one solves the Pearson equation in the dual space in terms of the functional, and introduces like an ansatz as a finite sum, one can obtain like a series of condition of the omega and also on the SL and SR, which are like the indices that denote the finite sum, which are simply these two conditions here. So the omegas, they must be related that way in terms of that lambda that I define here, right? Only so that you see it. So it's written in terms of the phi and the psi and the lattice, of course. And then there is like this boundary condition in the lambdas. So that boundary conditions give us the possibility of defining this kind of U. And what happens in the Paragratio and the Pararaka and the Kupararaka is that there are like two sets of SL and SR that satisfy the boundary condition. That gives us two solutions of the Pearson equation, which are the U square and the U triangle that are defined here. And now if we also take into consideration that the Pearson equation is linear, so an arbitrary solution of the Pearson equation is simply like an arbitrary linear combination of these two functional that are kind of the the solution of the linear space associated to the Pearson equation. And well, that works for the rest of the families. I won't be showing the results. And well, there is like a particularity here that is related to the fact that the Pearson equation is, well, there's like some condition that forces the fact that there are like two solutions. Usually there's only one, there's like uniqueness, but I won't go into details. And that is mainly all I wanted to talk. This is like some selected references. So those were the papers in which these parafamilies were defined. Well, the other were some standard references, and there's some points that I have been talking about. And that is all I wanted to say. Yeah, thank you.
Thank you so much, Guillermo. Maybe we can have time for one question, one quick question.
Thank you. A very naive question from a non-specialist. So I would associate classicality with certain set of properties like three terms, relation, whatever, which just somehow look similar in all families. So do I understand correctly that these all para-families also fall in the same set of properties?
Okay, like what I wanted to like transmit is that classicality is usually associated to the fact that a family satisfies like a differential equation with respect to some derivative that could be defined like in the continuous case, the usual one, or in a discrete way with respect to different lattices. But the fact that this family is classical with respect to some lattice doesn't mean that the orthogonality representation can be written in terms of that lattice. So here, the orthogonality was written like in terms of sum of two linear lattices, but then it wasn't classical with respect to this classic, with respect to a lattice that is a combination of two linear lattices. It classical with respect to other much simpler structure that is like only one linear lattice that actually has nothing to do with this description. So the thing is that this is like merely descriptive way of forming the orthogonality, but doesn't represent anything intrinsic algebraically of the family of polynomials.
Thank you so much. Because of time, we're going to continue with the next talk. So we thank Guillermo again. And our last speaker is Kenny Castillo. And I don't know what's happening, so we'll start in 1 minute.
Thank you. Oh. Well, I'm really sorry, and as everybody know, I always use Blackboard, but this one is extremely small. So I use my iPad, and I wrote my talk. Okay, my talk is intended to be followed by first years undergraduate students. So I'm sorry, but it will be extremely basic. Let's go to start with age, a non-zero complex number, and let's go to think in a sit in the complex plane with this easy property. U plus a is fixed over 2 times integers is contained in this